Sir? Sir?
Yes, I'm on. I'm here.
Sir, do you need to do a trial of the presentation?
Yeah. It will be nice actually if we can try. It looks some difficulty here.
So there is an
Just one
option at the bottom, present now. When you scroll down,
second. अब आएगा ना? Yeah, present now. Yes, it is.
present
Here.
now.
Yes. Then
So from there you can present your screen.
present your screen share.
Share your screen. Oh, an option is there. Oh, sir, it's coming. PPT is there.
देख नहीं पाऊंगा तो क्या बोल रहे हैं शुरुआत में तो okay.
Sir, it's visible, sir.
Okay. Perfect.
Sir, we'll be starting shortly.
Yeah, I'm ready for.
Okay, sir. Good morning, all. It gives me great pleasure to extend to you a very warm welcome on behalf of Department of Electronics of Kochi Institute of Science and Technology to the first session of Phase 2 of the fourth day of AICTE-sponsored 6 days short-term training program on the topic Trends and Technologies in Antenna Design and its Research Scopes. Today's session is on the topic RF absorbers, anechoic chambers and its application by Mr. Mahesh Chandkala. Mr. Mahesh Chandkala, the CEO and the founder of JV Micronics Faridabad, has more than 20 years of experience. He worked as a vice president of product development and business head in Lambda Microwave Private Limited Faridabad and director technical of Avia Prom Solutions Private Limited, Delhi. He is a member of Society of Indian Defence Manufacturer and Confederation of Indian Industries. He was associated with a number of projects such as development, installation, and commissioning of RCS measurement anechoic chambers to DLG and DMSRDE, DRDO Labs anechoic chamber for aviation MRO, that is Aviatech Enterprises, GOA for testing of radar of MiG-29K, Indian Navy fighter aircraft and electronic warfare equipments for Bharat Electronics Limited. He was awarded by the Times of India for Make in India and was facilitated by Minister of the State MMSC Sri PC Sarangi for celebrating 50 brands which are building the nation in the category of EMI, EMC, anechoic chambers and RF absorbers. Now, I hand over the session to Mr. Mahesh Chandkala.
Good morning and thank you very much. It's my pleasure to have my slides, my presentation for your prestigious institution and for this nice fine morning. I'll start my presentation that is RF absorbers, RF anechoic chambers, and its application. RF absorbers, which I'll be covering, is mostly related with anechoic chambers. Few slides about the background and of our company. We are incorporated in 2011. After that, after completing 9 years, we have supplied, manufactured, designed, and these are anechoic chambers and absorbers for various labs of DRDO, Indian Space Research Organization, Hindustan Aeronautical Limited, Bharat Electronics Limited, Samir, EQDC, BARC, ECIL, Indian Air Force, various IITs, NITs, IPR, and many private and government colleges in India. Private companies into manufacturing of antenna and related electronics equipment. Some are Astra Microwave Products Limited, Avantel Limited, Huber Schuner, Defsys, and many more. Not only we are limited to India, but we are also exporting our products to United States of America, Poland, Turkey, Canada, Netherlands, Belgium, Vietnam, and few more. Presently, we are proudly to announce that we are number one in the country as we have supplied highest numbers of RF anechoic chambers in India during our these 9 years of operation. We also have a foreign collaboration for the technology, especially for the products of near field test ranges and compact antenna test ranges. These ranges are built inside the RF anechoic chambers. As it has been explained that we have been awarded by the Times of India and the Minister of State, Mr. P.C. Sarangi, for Make in India concept, and that is for the celebration 50 brands across industries that are building the nation in the category of EMI, EMC anechoic chambers and RF absorbers last year. He is Mr. P.C. Sarangi, who is facilitating our company. Now, come to the topic. We'll start with RF absorbers. As I shared, these RF absorbers, which I am covering in my presentation, are mostly related with RF anechoic chambers. Most favorable RF absorber is a pyramid-shaped RF absorber, which is used inside our RF anechoic chamber, and we could develop from 200 megahertz to 110 gigahertz. See, these pyramidal absorbers can be developed from any frequency, but if you are developing from very low frequency, say like 30 megahertz, then the length of the pyramid, the height of the pyramid will be very, very high. Normally, most appreciable size is from 4 inches to 45 inches. And the attenuation of this RF absorber, that is absorption property, we call this as a reflectivity that is above minus 50 dB. Power handling of this RF absorber is also very, very important because inside anechoic chamber, sometimes we are radiating more power. So one should select RF absorber on the basis of the power usage also. The capacity of these RF absorbers, which we can see here, is from 1.5 kilowatt per meter square to 3 kilowatt per meter square. Another absorber is a wedge-shaped RF absorber. This absorber is also used inside the anechoic chamber. That is also working from 200 megahertz to 110 gigahertz. This reference of frequency I am given in terms of mostly used anechoic chamber in the world and in India. Of course, you can use these RF absorbers for terahertz frequencies also. Again, the dimension and the property and the power handling also remain same as we have in the pyramidal shape absorber. There is a walk-on absorber. Sometimes we have to walk over radio frequency absorber. Then we make a solid piece of absorber. that is also working from the same frequency band. Its height also matters from 7 inches to 45 inches, little bit different from other absorber. It is more higher. Reflectivity, no change. Power handling, no change. That is from 1.5 kilowatt per meter square to 3 kilowatt per meter square. Convoluted shape absorber. Convoluted shape absorber works from 1 gigahertz to 40 gigahertz. In some of the anechoic chambers, it is also being used for 100 gigahertz. And the thickness also goes from 4 inches to 6 inches, now up to 10 inches also. The reflectivity is better than minus 40 dB, little less than the pyramidal shape absorber. Its power handling capacity is 1.5 kilowatt per meter square. Here's an example of walk-on absorber. This is an RF anechoic chamber, and these are walk-on absorber which are placed over here. So we have to walk from door to this antenna under test, or from the transmitter to this antenna under test. That's why we are having these solid blocks called as walk-on absorbers. Another absorber is a multi-layer broadband absorber. It is in addition to the RF anechoic chamber. These absorbers are thin absorbers. The thickness varies from 1 inch to 2 inch. Sometimes it is 10 inches also, as per the reflectivity and as per the customized requirement of the user. Mostly it is from 1 inch to 2 inch thickness. These are multi-layered, hence it is working in the broadband from say 500 megahertz to 73 gigahertz. Now recently we have developed up to 110 gigahertz also. Its reflectivity will have a constraint. It will be around minus 20 dB. Power handling capacity is 1.5 kilowatt per meter square. This one, which is a blue color, is having a 1.5 kilowatt per meter square, and the material is different for it. It is having a big holes. Pores are bigger in size, and the material is also changed. So it is having a handling capacity of 3 kilowatt per meter square. Another absorber is a composite absorber which have been developed. It is a flexible rubber absorber. It is from 2 gigahertz to 75 gigahertz. The thickness varies from 1.5 mm to 50 mm. Reflectivity equals around 18 dB. Power handling capacity is up to 3 kilowatt per meter square, and it can also withstand very high temperature. These absorbers, which I'm telling about the frequency, these frequencies are not limited. We can design and we can develop absorber as per our frequency need. More high power absorber, when it is about 3 kilowatt per meter square, it is 10 watt per inch square. It is very, very high. This absorber is having a honeycomb type holes, and that will be used for dissipating the heat energy. It is used for very high power application inside anechoic chamber. Weatherproof RF absorber. Sometimes we researchers do activities in the outdoor also. So the absorber which were discussed before this slide were only indoor absorber. Now outdoor absorbers are also there. These absorbers were having a coating of a plastic material. So when a rain falls, it will fall down. It will not enter inside the absorber. When dust comes, you can wash it with water. Water spray can be done, and the absorber will look very new. Again, the development is from 200 megahertz to 110 gigahertz. All these absorbers, which I'm showing you, are very much part of industry and in research labs. Again, the thickness varies from 4 inches to 45 inches. Reflectivity is better than minus 50 dB, and the power handling capacity is up to 3 kilowatt per meter square. Other type of a weatherproof absorber, you can put absorber inside this block, and a block will be seen like this. The block is a RF transparent material whose dielectric resembles around 1. This block will be housing an absorber like this. So it's a plain block that is also used for weatherproof absorber that is for the outdoor application. In India, many places these weatherproof absorbers are used. Now, an echo chamber. An anechoic chamber is a shielded room which is designed to attenuate weight. What this anechoic chamber will do? It will not allow outside signal to come in, not allow inside signal to go out. In addition to that, it will be absorbing the reflection from the internal surfaces of the room and which will make it a non-echo. This anechoic chamber is used for two applications. One is for acoustic and another is for the RF. And the RF anechoic chamber will be suppressing the electromagnetic wave from the internal surfaces. And that is also called as sometime non-echo chamber. What we need inside an anechoic chamber? What are the properties one should consider while designing, while making, while considering the anechoic chamber? These are two very important properties. One is shielding effectiveness and other one is a reflectivity of anechoic chamber, that is also a quiet zone. We will take up these properties one by one. Let us first discuss the shielding effectiveness. Shielding of the chamber limits RF interferences. From where? From the equipment, from the source, which are located outside the chamber. It will not allow outside any noise, any signal to come inside the room. It doesn't allow inside RF signal also to go out. Sometimes we are working in high power. Sometimes we don't want to get affected with RF signal also. Sometimes our equipment are getting disturbance while we are working in the open air. There are many reasons for arresting the RF signal. That is, we are arresting by using a shielded enclosure, and the property is called as shielding effectiveness. It is basically an isolation between inside and outside of an anechoic chamber. How we can obtain it? How we can make it? We have to make a metal room by using iron, galvanized iron. Galvanized iron means an iron coated with zinc. Then aluminum sheets, copper sheets, any type of material will form a better shield. But we need to see how to use and which material to use. Depends upon the conductivity of a metal. And then the cost, how much we have. Certainly copper anechoic chamber will be costly. Now, shielding effectiveness is the requirement of user to select its limit. In modern time, it may normally vary from 50 dB to 110 dB. Because so much RF noises are present around our environment. Hence, we need a very high level of shielding effectiveness. For EMI, EMC testing, we would go up to 100 dB, 110 dB. But for antenna testing, antenna related testing equipments, we should minimum have 50 dB. I remember when we did first anechoic chamber for one of the organization around 20 years ago, that time shielding effectiveness was only selected as minus 25 dB. But now slowly it increased to 40, then to 50 dB, then to 60 dB, 70 dB, and now mostly in the antenna anechoic chamber also 80 dB is minimum used. When you go for the compact range, for higher application anechoic chamber, that time you should need 100 dB also up to particular frequency, and above up to it's 80 dB. Now, what types of shielded chambers in modern time? It depends upon the type of panels for construction of walls, roof, and flooring. It is a 2 mm thick normal galvanized iron sheet. We can weld and form a shielded structure. Another type, we can make a modular sheet, panel modules of 2 mm thick of GI sheet, which can be joined by using hardware and RF gaskets. Another type is a sandwich panel, which is made up of GI sheets, having wood in between the two GI sheets, that is also joined by GI profile and hardware. Here, 2 mm thickness. Why I am specific? that the conductivity of 2 thick GI sheets will be giving a shielding effectiveness of level up to 120 dB. It is proven for higher shielding effectiveness requirement, we can go up to 2 Welded structure. A cage made up of mild steel, pipes, angle, beam. Then over that is a GI sheets that is to be welded, and a nice welding structure is constructed. Welded structure pipes, beams, and angles. You can see here formation of the cage, which is the first step of making the chamber. These are the beams which are welded. A more better look of this, a cage formation, and a cage will look like this. Then I'll go back. This cage is having MS structure as well as GI welded sheet. So this is welded structure. Now, a pan structure. Pan modules are preferable sometime. Sometimes we have to change. We need to change the location of anechoic chamber. Some of the user, they are working in old buildings, they want to go to new buildings. Sometimes they want to increase the size of the chamber. In that situation, pan modules are preferable. What is pan module? It's a simple GI sheet which is cut and given a bend of 90 degree and another bend of 90 degree. There are two bends of 90 degree having cutouts for fixing the hardware like nuts and bolts. You can see here practically, these are pan panels. You can see this small pan panel on the top. It is having one band, then second band, and these are the cutouts for fixing hardware and gaskets. Two pan panels at the corner. These are nuts and bolts. In between, there is a double bulb gasket. It's rounded at two ends. That is very, very important to understand. And in between, this bolt will come in and it will be joined by using the nuts. You can see here example of pan panel. This chamber is getting ready. These many pan panels are fixed on it. So these pan panels will cover all around and form a proper sheet. Shielded structure using sandwiched panel. It is a wooden board sandwiched between two GI sheets. And together by
Hello, sir. Sir, excuse me. Sir, voice is breaking. At times, it's not audible.
they are more popular in EMI. Yes, please.
Excuse me, sir, your voice is breaking. Mm.
Am I audible, madam?
Yes, sir. Yes, sir.
Okay. I've changed my network.
Okay, sir.
So,
Now it's audible.
yeah. Do you want me to go back?
Oh, sir.
Okay. I'll start from this slide. You can see here, these panels are joined together and they are becoming a part of anechoic chamber, shielded chamber.
Sir, can you go into slideshow?
Oh,
There is
sure,
no.
sure. Sure.
Okay, sir.
Yeah. Is it fine, ma'am?
Oh, okay, sir. Thank you.
Okay. So this is panels which are joined together and they are forming a part of anechoic chamber. It will be fixed all around this and a perfect shield will be formed. Shielded structure using sandwich panels. These are wooden boards sandwiched between two GI sheets. Sandwich panels are joined together by using profile beams and RF gaskets. These sandwich panels are more popular for EMI EMC shielded chamber. Let us know, we should know that in India, most of the chambers and popularity we have, that is for the welded chamber and for pan modular shielded chamber. But let me also explain you how these sandwich panels looks like. These two are wooden boards, and over that we have a GI sheet here all around for this also, and then these two are joined by using this fixture. In the corner, it will look like this. In between, there is a wood. Actually, in India, we have a problem of wood because all woods are when they are affected with moisture, they get bulge out. So we're not able to make in India sandwich panel because of this problem. Because after some time, maybe after 2, 3 years or 4 years, especially maybe on the coastal areas, this panel gets bulge out. It was experimented earlier, so hence there is no further work has been done on this. So let me explain how shield is created. This is a shielded room, which is made up of now GI sheets and mild steels, everything we have learned. What will happen when RF is striking on it? Some portion will get reflected, some portion will be induced, and that will be grounded. One should have a perfect ground for shielded chamber. This grounding should be separate. This grounding should not ground a building. It will create noise. This should be less than 2 ohm. Somewhere, this earthing resistance is also for EMI EMC application. Should use only copper strips, not GI strips, not aluminum strips. Copper is the best source for making a perfect grounding. What are the accessories of shielded chamber? Especially when we talk about shielding effectiveness. It's RF shielded door, very important component. Honeycomb air conditioning vents, power line filters, access panels, emission-free lights, emission-free CCTV camera system. This guy is especially for EMI MC. For normal anechoic chamber normal means I mean for the antenna chambers and where shielding effectiveness is little bit less. There we can use non-shielded CCTV cameras also, and then RF gaskets. Shielded door. See, shielding effectiveness of shielded door is achieved by, very important, by mating the brass knife edge extrusion. The door should be having a panel of knife edge extrusion of the door leaf, and then it should go in the concentric rows of beryllium copper finger stock. One side, it is a knife edge, another side, it's a copper finger stock. I will show you photograph also. The importance of the door is the shielded room is only effective when the RF door is manufactured to provide the attenuation characteristics equal to that of the enclosure. You can see here, this is a shielded door. One end, this panel I have shown here, this part is a knife edge here, and this part is having a beryllium copper finger gaskets. These are here. This knife edge will go inside it, and the beryllium finger, which is having a very high elastic property, will be holding this knife edge, and it will not allow RF to go in because there will not be a pinhole when the knife edge goes inside the beryllium copper finger gasket. Another one is a power line filter. When we are bringing electricity inside the room, especially for lightning and for other application, sometimes some anechoic chamber keep equipments also, there is various requirement of electrical power line inside the room. If you are directly taking those power line inside the room, then those power line will behave as an antenna. Hence, we have to avoid this antenna because it will create a noise. Hence, we are using power line filters for carrying this electrical line inside the anechoic chamber. This is an example of power line filter which is directly mounted on the wall. You can see here, these are two filters. One is smaller, directly mounted on this, so the ground to ground is matching, and if at all there is a RF which is striking on this box, it will be matching with the ground of the shield, and that will be grounded. It's very important to fix RF power line filter directly on the body of shielded chamber. Honeycomb vents for air conditioner. We cannot directly put AC openings so that cool air comes in. We have to put some vents. These AC vents are nothing but waveguides, which is having cutoff frequency from minimum to the maximum. And the waveguides are the shape of honeycomb. Why we need? Because we have an opening. First question sometime people may have, why we need air conditioner? We need air conditioner inside the anechoic chamber. Why? Because, let me give you an example. If a small amount of RF is penetrating at a particular point, it will generate enormous amount of heat energy. Its RMS value will be very, very high. So that heat energy can create a very high temperature and can burn the absorber also. So we need to cool down that. We need to have a cool temperature inside the anechoic chamber. Another reason, the life of absorber will also increase. How it will increase? We know that the RF absorber, especially which are fixed inside the anechoic chamber, or we are discussing about, they are made up of foam, and foam is impregnated with the chemical, the carbon. What will happen during summer season? The molecules will expand. During winter, the molecule will compress. So because of this reason, there will be a vibration, there will be an oscillation. Hence, the molecules which are bonded on the foam will be getting loose or in a condition. Temperature will only keep so for this because we have very high summer, we have very high winter. You see how is are fixed on panel. These are the panels. They are panels. If my voice is clear or is it breaking? Am I audible, madam? Can you hear me?
Yes, sir. Yes, sir.
Okay, thank you very much. Now, moving to another important accessory of anechoic chamber is access panel or penetration panel or cable entry plate. These are various names of these accessories. We have to carry RF cable and another cables inside the chamber. We cannot carry it directly because this cable will again act as an antenna. So we will be using input and output connectors. Suppose cable is having SMA connector, we will be using input and output connector of SMA. From outside, that cable will be getting terminated at this IO connector, and from inside, we have to take another cable for connecting it with our instrument. It is also very important accessory for RF anechoic chamber that is connected near to the place where our RF engineers are sitting and monitoring the performance of the device under test. It should be very near to that place. We discussed about shielded door. You can see here, this door is having two knife edge housing. So for very high shielding effectiveness, we use two knife edges on the door. These two knife edges will rest in these two portions. It's honeycomb vent. We started now. These are power line filters. We said like it should be pasted on the wall itself. You can see something new here. These are pipe penetration. For some of the specific application, inside the chamber, we would need cool air and a cooling liquid. How can we take it inside? Whatever pipe we are using, that has to be a metallic one. And again, a metal structure of honeycomb shape with a cutoff frequency will be inserted inside this pipe. And then we can carry cool air or cool water inside for reducing the temperature of source or anything. EMI RFI cable entry glands. For EMI EMC anechoic chamber, when we are carrying cable inside the chamber, it should have a shielded gaskets like this. A perfect shielding effectiveness should be there. Say at 10 kilohertz, it should have 70 dB and above. At 100 megahertz, it should have 120 dB and above. That much shielding effectiveness is required for EMI EMC chambers. Other accessories are CCTV camera, which are required to monitor the outgoing measurement of DUT inside the anechoic chamber. Whatever we are testing inside anechoic chamber, one has to see that. We need to see what is happening inside the DUT. Is it placed in the correct place? Has it not fallen down? Is it the antenna positioner is rotating properly in all the axes? Whatever command has been given. So everything has to be monitored. CCTV is a very important accessory which one must install in his or her anechoic chamber. Then emission-free high-end camera system is mandatory for EMI EMC. But for RF and anechoic chambers, the shielded EMC cameras are not mandatory. Even in the EMI EMC chamber, the field is very high. Sometimes the field is 200 volt per meter. That CCTV camera should able to withstand this 200 volt per meter. Fire alarm and smoke detectors. Fire suppression system. Nowadays, in modern anechoic chamber, we are using gas-based system. These gas-based systems are very costly. Earlier, water sprinklers were used, but those water sprinklers were damaging the RF absorbers or the equipment which were kept inside the chamber. So it has been now replaced with gas-based system. And it is so much modernized, so much research has been done that earlier this gas was poisonous, but now environmental friendly gas is also coming. But again, I told you these systems are very, very costly. But whenever it is required for some application, and it has been used in India also. We have installed those systems. Now, shielding effectiveness of the chamber is so, and that will be provided by the RF absorber. The internal appearance of whatever we have made is to be aligned with these RF absorbers. Sometimes is also called as radiation wave on the absorber and then receiving it. Suppose a 10 dB RF power has been given to the RF absorber and we have reduced it. We received the RF energy of minus 30 dB. That difference of the value is a reflectivity. 10 minus 30 dB is 40 dB. That means the reflectivity of RF absorber is 40 dB. That means the energy is shortened by minus 40 dB. That means energy 40 dB is absorbed by the RF absorber. You can see here a reflectivity chart which is dependent on frequency and height of the RF absorber. Height matters a lot in case of RF absorbers. Let us say an example of JVM FU18. This model 18 is the height of absorber at 400 megahertz. It is giving a reflectivity of minus 28 dB. At higher frequency 3 gigahertz minus 44, and above it will be above 50 dB. On the table we have written 50, but it goes up to 55, 60, 65 at various higher frequencies. At 40 gigahertz and above, we have to again characterize the absorber. Sorry. Common types of radio absorbent material for anechoic chamber. We studied about PU foam absorbers, which are from 200 megahertz and above, gigahertz and terahertz. For EMI EMC chamber, where we have to work at low frequency also, we will be using ferrite tile absorbers, which will be from 30 megahertz to 1 gigahertz. What will happen above 1 gigahertz? What we will do? We will make a hybrid absorber. That will be from 30 megahertz and above, whatever upper range you want to use. How it will be done? These are our pyramidal shape absorber. This is our ferrite tile. Over that ferrite tile, we will be pasting this pyramid shape absorber and it will be a hybrid absorber. Performance of these RF absorber. These pyramidal absorber, they are most efficient when the incident wave is at normal to the internal chamber surface, when the pyramidal height is approximately equal to lambda by 4. See, this pyramidal shape absorber, wedge shape absorber, or mostly different type of absorbers are designed on quarter wave principle. Lambda by 4 should be the minimum height of the absorber, where lambda is a free space wavelength. When we are increasing the pyramidal height of absorber, that means we are improving the effectiveness of the chamber at low frequencies. At low frequency, the wavelength is high, so we have bigger size of RF absorber. Size here means height of absorber. When we go to the high frequency, then the wavelength is reduced. Lambda by 4 will be more smaller. That means for high frequency, we can make smaller height of RF absorber. It is very important concept we have to understand. Again in this slide, I'm showing the height versus frequency. The height of the absorber determines its lowest frequency of operation. At lower frequencies, the wavelength is large. See, these three high absorbers are shown here. When you want to construct your anechoic chamber from the lower frequency, then bigger height absorber. When you want to construct your chamber from 20 gigahertz and above, then this size of absorber. Suppose you're planning to make anechoic chamber only for millimeter wave, only in W band, then the height of absorber will be like this. Height is directly proportional to the lowest frequency. We have to remember, suppose if you are looking only W band chamber, then we can go for very small absorber. Suppose we are working for telecom frequencies or lower frequencies, then we need to have bigger size of absorber and bigger size of anechoic chamber and bigger room requirement of anechoic chamber. This I've already explained. Now, testing of RF absorbers. These are to be tested as per IEEE 1128 of 1998. What it is? This is a complete RF anechoic chamber. The test is called as NRL Arch method. NRL stands for Naval Research Laboratory of USA. So it is an arch. You can see here, there are two antennas. One is transmitting antenna, one is receiving antenna. This is a device means our absorber under test. Below this, a conductive sheet that can be aluminum or copper or GI. Here is a metallic stand. RF energy is transmitted by antenna. First, there should not be any RF absorber placed on it. The energy is received and recorded in the receiver, in the VNA, in spectrum analyzer. And then we put our RF absorber on it and see how much it has been reduced. The difference is the reflectivity, and that is the property of RF absorber. These two antennas are rotating from here to here, here to here. They rotate together, and we need to see the reflectivity at various angles. How we decide this height? This height is a far field distance, which is 2d square by lambda. In this situation, the distance from this horn antenna to the plate and from this plate, metal plate, to this horn antenna, we add together, and this is a far field 2d square by lambda. We are varying this height, we are varying this far field distance by varying the height of this metallic stand. This way, these RF absorbers are tested in anechoic chamber in RL arch method. You can see here, this is an anechoic chamber, what we have in JV Micronics. These are two low frequency horn antennas of 500 megahertz, and we are testing this absorber. One test was fire reflectivity of absorber, and another test of RF absorber is fire retardancy test. Fire retardancy test is very, very important to understand about this RF absorber. May not be the liking of RF engineers, but we should understand because it's very, very important property of an RF absorber. Again, the standard is NRL 8093, that is Naval Research Laboratory of USA, serial number 123. These three tests are mandatory. This is the most stringent test of fire retardancy, which is used all around the globe. First test is resistance to electrical stress, how much it is resisting the electrical stress, that means sparks and all, electrical spark, short circuit and all. Ease of ignition and flame propagation, how much absorber is resisting the flame, and the third is a smoldering test. I'll tell you all these tests in little way. This is a resistance to electrical stress. This is a sample of 6 inch by 6 inch and thickness of 2 inches. It will be inserted with a naked electrical wire having 240 volt AC and 8 ampere, not 5 ampere. Please remember, it should be 8 ampere. And then we are switching on the power supply. If there's a spark, see, there might be a spark because carbon is impregnated on this and it behaves as a conductor sometime. So it will be a spark. If there is a spark, then the fire should get extinguished within 1 minute. If the fire is getting extinguished within 1 minute, then absorber is a fire retardant. Let me tell you the definition of fire retardant is, in case there is a fire, then absorber should get extinguished by its own. That is the fire retardant property. Another experiment, another test, ease of ignition and flame propagation. We take a block as per this standard of 2-inch cube. This 2-inch cube block is placed over Bunsen burner, and the Bunsen burner, which gets a temperature of up to 1900 degrees C. That much heat is given to this small cube of 2 inch for 30 seconds. We remove it after 30 seconds. When we are giving the heat, this block, this cube will be burning like anything. After removing the heat, after removing the Bunsen burner, this block should get extinguished itself within one minute. You'll be surprised. Whatever RF absorbers we are supplying are having all these three tests approved. Third test is a smoldering test. We take a block of 8-inch cube. This 8-inch cube absorber will be inserted with a heater rod, which will be heating up to 600 degrees C. Thermocouple is attached with it. There is another thermocouple which will be inserted 1 inch apart. What will happen? We will slowly start heating up this heater. We have an electrical automatic complete test system here. This temperature will be displayed up to 600 degrees C. That means heater will be heated up to 600 degree temperature. After 600 degree temperature, the temperature should get arrested. We'll switch off the power supply in such a way there will be other side that will be keeping the rod up to 600 degrees C. If temperature going down, power supply gets on. If temperature goes down high, it will switch off. This activity will remain there for 5 minutes. That means for 5 minutes we are heating this block up to 600 degrees C. And the important, interesting thing is this heater is inserted up to 3 inches. And then after 5 minutes, we'll switch off the power supply. After that, this thermocouple will get operated. It has a sensor and this thermocouple will go off. We will be monitoring the temperature of this block in the absence of electrical power supply. in the absence of the increasing heat, but already existing heat in the heater, anytime if this thermocouple gets more temperature above 450 degrees C, then the block is failed. Very, very stringent and tough test. It means if there is a fire inside the absorber which is remaining due to any reason, then that fire also should get extinguished itself. Please remember to buy RF absorber which are cleared for the test. You can go and witness at the manufacturer place also. We always invite our buyers or user or researcher to come and witness these tests. All tests, whatever you want to see. Now, very, very important for the researchers, how to calculate the size of anechoic chamber. How much size, what is the length especially they are looking for. How it will be decided, we are discussing about the far field anechoic chamber. The far field distance is 2d square by lambda. Here, d is the maximum dimension of your antenna under test. Please consider the antenna or the device, whatever you are designing, whatever you are going to develop or to produce, the maximum dimension of that device. It may be a diagonal, it can be a length, it can be a width, it can be a height. That dimension is a d here. Accordingly, you calculate the 2d square by lambda. Lambda will be important because you have a various frequency band for which you want to test. That far field distance is to be calculated for lowest and highest frequency of anechoic chamber. Both the frequency band you have to see, lowest one also and the higher one also. Because this distance will change, and whatever bigger distance comes, that should be the length of your anechoic chamber. Addition to that, not only the far field, you have to add some more distances. And then that you add, for example, distance plus 8.5 feet. Case of this chamber start from say this 1 feet high absorber. But what we have done in this particular case, we have fixed this transmitting antenna on the wall of the chamber itself, so that we are reducing the length of the chamber. Otherwise, in other you can place directly after some distance from these absorbers, then you can make a transmitting mast here and put the antenna on that. Transmitter wall, we have seen one roll positioner on the wall, then there is an antenna. So this distance is in addition to the far field, from antenna to positioner and up to this place. So this is coming around 1.1 to 1.5 feet, and again this one the same. So the total is around 2.5 feet we are going to add in the far field. What will happen in the receiver side? In the side where you are keeping your device under test, you will be keeping your device on the center of the positioner. Then there is a walk-on absorber on which we will be standing and working on this positioner and working on this device. And then there is a wall here. There are various tests for which we need to keep the device under test little away from this tip. Otherwise, those tests will be getting failed. So a key distance is being made between tip of the absorber and your device under test. In this situation, where we are using 1 feet of absorber, we can see height of absorber is 1 feet, then 2 feet is this absorber, it becomes 3, 2 feet for Viacom 5, 1 feet for this, 6 feet we are adding more. So That was distance calculation. Now here is a quiet zone. Quiet zone is a zone where we keep our device under test. And the quiet zone is decided on the basis of the dimension of our device under test. It's very, very important. It is defined volume with the chamber where is for evaluation. It's a most often used access. Quiet zone inside the chamber, but now is moving a phase versus linear position data with astronomy signal. That some facts we should know. Bandwidth of the chamber, all this we have discussed. Bandwidth of the chamber is a function of far field requirement, maximum dimension of AUT or DUT, size of the quiet zone that is desired, types of the absorber we are using. The antenna under test must be in the far field of the illuminating antenna. Illuminating antenna means a transmitting antenna. Generally, chamber operating at low frequencies tend to be quite large. We have discussed some of these facts, and now we will be finding the quiet zone probe. Here we are. This is a quiet zone probe. It can move in various axes, linear axis, azimuth axis, and roll axis. This is a probe antenna. This is standard gain horn. Its properties are already known. This guy is helping to test your antenna also, but here we are testing the quiet zone. It will move in the volume of the decided quiet zone. Quiet zone is decided as per the volume. It can be a cubical shape, it can be a cuboidal shape, it can be a cylindrical shape, it can be a spherical shape. You can see here, this is the quiet zone probe. We have to test all around. You can see here, quiet zone in the circular fashion. This one is a spherical one. Antenna will look 90 degree, 45 degree. This way, this antenna will be rotating, and we will be keep on noting down the figures, whatever we are receiving in our receiver. Here's anechoic chamber. You can see here, this is antenna positioner, this is source antenna, and various equipments which are connected. Testing of anechoic chamber. That quiet zone test, what we are doing, that is a free space VSWR method. We will be using a source, an horn antenna, horn receiver, quiet zone probe, then spectrum analyzer. You can see here, first we'll be noting down the line of sight, the maximum RF energy received, then RF energy received from various angles. All these figures will be noted down. These are the steps for measuring the quiet zone in the anechoic chamber. We have seen the block diagram. Raise the antenna height in such way that both the antennas should be in the center of front wall of the chamber. That means we are noting down the line of sight. Then after noting down the line of sight power, then rotate the antenna, say 60 degree left, 60 degree right, means various angles we have to rotate and note down the reflected power. Move the antenna in the quiet zone. Normally, what we do is the step size of the antenna in the volume should be, in the linear motion, it should be lambda by 10. That will give you a perfect reading the curve fit figures for recording. Note down afterward when the readings are known, we have to note down the peaks. That is the maximum peaks observed, and we will be maximum peak means where is the high rise and suddenly the maximum fall. That reading should be noted down, and then we note down and the minimum now shielding effective. Again, we have RF source, we have on for transmission, for what we do first, the testing particular distance will take given the how much distance or proceed, and then the difference of these two after door is closed is a shielding effectiveness. Door is very important. Please note down and always test the shielding effectiveness in front of the door. In your anechoic chambers, those academic or engineering colleges where you have the anechoic chamber, you can test your anechoic chamber for shielding effectiveness. Because sometime you need to check after 2-3 years, these shielding effectiveness are advisable to be tested, and all the other properties also. It is a data sheet of what we do the testing. Yes, now here we have antenna positioners. Inside the anechoic chamber, we'll be placing our antenna under test or device under test. This antenna positioner we can see here is a 2-axis. Other side of this is here. This will rotate like this, which will be an elevation movement. One here, it is azimuth. 2-axis. Third axis will be on the transmitter side, which will be a roll. Normally, what we do is we put automatic axis on the transmitter side, which is a single, and 2 axes at the receiver side, which are 2 axes. In case when it is desired to have a 3 axis on the same place, then 3 axes can be given. This roll positioner will be fixed on here on the top of this azimuth, and it will become a 3 axis. When you want to make a linear movement also, as we have shown in you in the quiet zone probe, then a linear movement of left and right and front and back can also be given. But as per our experience, this 3-axis positioner is perfect for doing all the measurement inside antenna anechoic chamber. We have 2 types of control units. One control unit can be fixed on the rack, 19 inches rack, standard 19-inch rack, and another one is kept as a desktop on the tabletop. So by using this antenna positioner, we are testing our antenna. It is a metallic, it can be non-metallic also. For various specific purposes, we have 2 different types, non-metal and metal. If at all it's a metallic, we'll make it less reflective by using RF absorbers. Again, somebody may be thinking like, if you are keeping this antenna positioner on the ground, no. It is not kept on the ground. I'll show you some photographs also. These positioner will be kept on tower, and the height of this positioner is again dependent on the quiet zone and the center of the anechoic chamber. Quiet zone will also have center in the center of anechoic chamber. In the front wall, wherever there is a center point, that will be the center of quiet zone. That will be the center of antenna positioner. So what all software, what all measurement you can do? We can do 2D plotting, 3D plotting, we can do gain, reference antenna import features, we can measure S parameters, multiple trace plots, then vector plots, various frequency measurements, antenna efficiency, axle ratios, cross polarization, co-polarization, all these can be done by using our antenna positioner and software. These software can be easily connected with VNA or signal generator or spectrum analyzer. Whatever you want, your instrument can do handshake with this antenna positioner and software. In addition to the control unit, these features can also be done from the laptop itself. So both the things are doing the major recording. One is a laptop in the having a software, other one is a controller. Now we come to the scope of application of measurement of these are two important scope of
Excuse me, sir. The
objects
voice is
within
breaking.
aircraft
Voice is
or
not
on this
clear.
I have covered here. If these applications, yes, okay. How is the voice now?
Now it's audible, sir.
Okay. So I was telling about the scope. We have discussed these scopes that the most important application of anechoic chamber is the measurement of antenna radiation pattern. Second important is electromagnetic compatibility. These two are the basic two important application of RF anechoic chambers. The recent studies which are being done by many researchers, they are working in India on this, that is a radar cross-section measurement. Testing can be conducted on full-scale objects, including aircraft or on-scale models, where the wavelength of the measuring radiation is scaled in different proportion to the target size. It is a most live research which is going on at this moment. I have penned down some of the application of anechoic chamber. Most of the applications are being done in India also, around the globe also. Mostly I have covered, but there are n numbers. Testing of RF and microwave antenna. Any antenna you want to test, better to test inside the anechoic chamber. Testing of telecom antenna like BTS. See, all these things are practically happening in industry at this time. BTS antenna, 3G antenna, 4G antenna, 5G antenna, and now research also started on 6G antenna also. These are the practical application where our RF engineers can work and they get the job opportunity also after finishing their research. Here I'm taking on those application only. Testing of ground radars, testing of radars of aircrafts, testing and developing antenna feeds, even testing of vehicles like aircraft, testing of automobile like cars, motorcycles, military trucks, etc. Testing of electrical vehicles. Nowadays, we are focusing to bring electronic vehicles. There's an urgent requirement of n numbers of anechoic chambers for testing the electrical vehicles. Testing of mobile phones, testing of laptops, because all these equipments are having antenna. Some device antenna for pattern, for so many properties, then device for EMI, EMC, your mobile phone, laptop, EMC, on this device. Testing of devices like routers, amplifiers, etc. Our numbers. Another application research on technology for space application, research and development of all projects related with RF and microwave in engineering colleges, testing of IoT, Internet of Things for telecom application, testing of any electronic devices for electromagnetic compatibility like electrical meters, transmitters, receivers, cables, RF cables, anything is to be tested. Even RF cable, what we are getting from the manufacturer, all these cables are tested inside the anechoic chamber, even for a very important property of VSWR measurement. That VSWR of RF cable is getting tested inside the RF anechoic chamber only. There are many such suppliers in India. Even they are manufacturing those cables in India and supplying to foreign countries, and then those branded cables are coming to us. Another application, there are various applications. LED lights. Why we need to test LED lights? See, LED light should not give a disturbance of RF. It should not radiate RF energy. That noise it should not do. So that is to be tested inside the EMI, EMC anechoic chamber. CCTV, whether it can withstand high RF, whether it is a source, whatever. Because CCTV also has nowadays amplifiers, and they also speak and they also record. All those things that needs a testing inside EMI, EMC lab. Power line filters tested inside the chamber. Honeycomb vents, Whatever I have covered in anechoic chamber presentation, all those accessories are again tested inside the shielded RF anechoic chamber. Those property, how can we vet? Inside the chamber only. Testing of drones for communication and other properties. You know, n numbers of tests are there on drones, n number of tests. Various researches are going on in the drones and all those inside the chamber. Various research and development programs of government needs anechoic chamber for testing products in present, income or incoming futures. Telecommunication. India is working on 5G. World is working on 5G. But now 6G. What 6G? It's a millimeter. It's 100 gigahertz. 6G communication, which still India need to heard about it, whereas research and planning has already been started in some countries, needs RF anechoic chamber. Academic researchers need to share the name and location. Sometimes they need to share the photographs also. You need anechoic chamber and many more all around the world. N numbers of applications are there. You just think on the basis of these lines, whatever I've shared. Now, let us see some of a spatial RF anechoic chamber for various applications. On the basis of application, I'll show you here. You can see here, this anechoic chamber is having a measurement up to 110 gigahertz. And this chamber is used for biological study. That is effect of RF on human. And it's there in India. All these examples I'll be giving on the basis of chambers in India, and that is manufactured by us. So you can see how many varieties of chamber will be there in addition to the normal academia and antenna chambers. You can see here, this chamber is with the bell, and it is used for testing electronic warfare equipments. Here I have shown a chamber photograph of one engineering college that is it is recently been commissioned, that is for Girls Women College, Engineering College in Ajmer. You can see here, this is antenna positioner and the tower here. I'll show you in another slide, this one. Here is an antenna positioner, 2 axes, how it is fixed on the tower. This tower is covered with RF absorber. So it is all equal to these absorbers. So the property of the metal has gone. Another side for transmitting, this is a roll positioner. That side was a receiver and this side is a transmitter. You can see here walk-on absorber and wedge absorbers pasted inside it. This another chamber is for RCS measurement, which we have supplied to one DRDO lab. You can see here, it's a pylon. It's the dielectric constant of it is equal to 1, and this is styrofoam. Beneath it is an antenna positioner, and this is a target for calibration sphere. Another anechoic chamber. This one is for testing. There's a wall in between anechoic chamber. This portion is having a full anechoic chamber, and that is a semi-anechoic chamber behind this. Semi-anechoic chamber means there is no absorber on the floor, and full anechoic chamber means there are absorber on the floor also, in addition to all the 5 faces of the room. The radar will come from this room and it will be placed like this, a radar cone, and the testing will be done in this anechoic chamber. It's a unique one, and there are many. Here is an aircraft anechoic chamber. It's also in India. Aircraft brought in by using this pulley mechanism, motor mechanism, and then the nose will enter inside this place. Inside that, there is a full anechoic chamber. This place, as aircraft to come in, there is no absorber on the floor. If you require, then absorber can be placed on the floor and then testing can be done. So it's an aircraft anechoic chamber. Even as your engineering college is in Kochi, I have one example that we have done RF anechoic chamber for one engineering college in Palakkad, one engineering college in Bangalore, near to your place, in IIT Madras, we have absorbers, then in Bell Bangalore, in Bell Hyderabad. In South, we have most engineering anechoic chambers in Hyderabad. Why I'm telling you, like if you want to see, you can see these anechoic chambers there, which are near to you. Now, after knowing about RF absorbers and application and anechoic chamber, we have to decide our own anechoic chamber also. Whoever is planning for anechoic chamber can go through the slides now, which I will be presenting to you now. We have to decide the length and width and height of anechoic chamber. We have to pen down what is the frequency we want to use. What is the purpose of anechoic chamber? See, this questionnaire can be sent to the manufacturer also. So you have designed your chamber yourself and then you are asking a proposal. That also can be done and you can design for your research also. Chamber shielding effectiveness, how much shielding effectiveness we will need. It should be tested with IEEE 299. Sealing support, whether we need a self-supporting structure or it is to be supported by the parent room where you want to fix the anechoic chamber. Number of doors, how many numbers of doors we want. Why we have written number of doors? Sometimes we need 2 doors. Sometimes we have a big anechoic chamber. Then we need 1 door to go and access our antenna under test or device under test, and another door for accessing our transmitting antenna. If somebody asks, then we have a standard door. All manufacturers have this standard door, 3 feet or 7 feet by custom. Most of the users, they need customized door, bigger door, or whatever. Some big doors, some chambers, they also go for the emergency exit door. That means they have more than 2 doors, 3 doors. What all input and output connectors we are looking for? It depends upon the type of cable we will be taking inside the chamber. For low frequencies, we will need BNC, NN connectors, SMA to SMA input output connector, and then above 2.94 and all those connectors. So that information is also need to be studied, like how many cables we'll be taking inside. Accordingly, we will need the input and output connectors. Do we need RF waveguide pipe penetration? I've explained you. Do we need RF honeycomb air vents? What shall be the size of my honeycomb vents? If you can find, it's fine. Otherwise, discuss with the manufacturer and we will guide you. Power line filters. See, as I explained you the importance of power line filter. How you will find it out? We should know voltage. We should know the ampere. For how many current ampere we would need this? What is the frequency of our operation? Means the electrical power lines. The home which is coming to home is 50 hertz or 60 hertz. And suppose if you have a 3-phase, some equipments where you want to test it inside the chamber, then we will need, it may be 100 hertz also. So we have to see for the power line filter, voltage, ampere, frequency, and whether it is a single phase or 3-phase. This information need to be shared. That will make the life easier for selecting the power line filters. Then some big chambers also need telephone line filters. Big anechoic chambers, they want to take telephone inside, but again, it should have a filter. Whether you need that or not, it is also required. Emission-free light points. How many light points we need? What should be the watt? Or what should be the lux? What is the intensity of the light we need? Sometimes we need a very nice, bright, illuminated anechoic chamber. We will go for more of bulbs. We'll go for high wattage of LED lights. Sometimes we don't. Sometimes we feel, no. I want only light on my device under test and one light on my transmitter. That time we have to discuss with the manufacturer or feel ourselves to pen down all those requirements. Whether we will need CCTV, yes or no. How many cameras we need? Suppose if you want to see only our device under test, you need only one. Suppose you want to see your transmitter antenna also, you need two. Minimum 2 numbers of CCTV camera or 1 number of CCTV camera depend upon the size of the chamber. Fire alarm system. It is mandatory to go for the fire alarm system. We have traditional alarm system as per your requirement. Fire suppression system. As I explained you, whether you need gas-based fire systems or no, if the fund is less, most of the time it is, then we'll go for the normal ABC fire extinguisher. 1 or 2 for small anechoic chambers are fine. For academy, I mean. Air conditioner, yes or no, it is in the scope of whom? In the manufacturer or yours? That is to be penned down. So all these things will help in deciding the budget of anechoic chamber also. Earthing less than 2. It is required whether you have a separate earthing point, unused earthing point in your premises, in your college or in your lab, then you say, I don't need earthing point, I will need only the copper wire and earthing stud for connection. Otherwise, yes, we would need complete earthing system. Need RF absorbers? Yes. If it is for anechoic chamber, it is yes. If it is only for the shielded chamber, then no. What is the height of absorber you are looking for? You can see the manufacturer's data sheet and then can put down. Normally, most of the anechoic chambers in India, for the academia purpose, I can say about 90%, they are 12 inches high absorbers or 9 inches high absorbers. Which model do you prefer? Write down here. Then what will be the size of quiet zone? So this is the factor which will be cross-checking the dimension of your required anechoic chamber. On which floor of the building you are building it? Why on the floor? Whether it is first floor, second floor, third floor. Why it is important? It is important to know that what will be the length of my copper strip and what is the condition of earthing. See, for EMI EMC chamber, you can only build in the ground floor. For antenna anechoic chamber and for other application anechoic chamber, you can go on second and third floor. For EMI EMC, we would need very high level, very nice earthing resistance less than 1 ohm. But for other, we can go for 2 ohm and less. So this is just to know like in which floor you are. Need antenna turntable with controller and additional PC controlling? Yes. Whether if you don't have antenna positioner or turntable, certainly answer is yes. At that time, you write yes. And number of axes, how many axes you are looking for? It is to be decided. Sometime one axis is also fine. 2D parameters. That's fine for me. Then one axis. If you want all the parameters, then you go for 3 axis. What will be the weight carrying capacity? Another deciding factor. Sometimes the device what you are testing, the antenna you are testing, sometimes it is heavy also. It's not the patch antenna all the time. It is heavy antenna, heavy device. That to be weighed and to be informed so that manufacturing can be done by taking all these consideration. What will be the diameter of tabletop of the positioner? Sometimes an array antenna, bigger antenna you are testing 1 meter across 1 meter. That means you need a bigger tabletop. So what is the accuracy we are expecting? For highly accurate devices, for some of the equipments, we would go for a 0.001, 0.01, 0.1. So such type of accuracy is also to be known and correctly understood, like what shall be, that is to be shared. Whether we need testing antenna and from which frequency to which frequency. Need standard horn gain antenna with the test report? Yes. Whenever you buy antenna, try to buy standard gain horns. RF cables required? Yes. See, why I'm explaining you, these questions will give you a complete information like what you want. I've seen in a recent anechoic chamber, one we have supplied to KLE University in Hubli. There, they have not used, they have not taken care of RF cable. Chamber was there, VNA was there, everything was there, but there was no RF cable. So it was lying. So please remember these RF cables to be noted down. What shall be the size? How you will decide? You will say you will be making a sketch of the chamber. You will be making a sketch where you will sit, where you will have a control room. That will be the deciding factor of the length of RF cables. What instrument we need, whether we need VNA or we need signal generator or spectrum analyzer. We need to buy, do we need for which different brand, Keysight, R&S, Anritsu, or whatever you like. Nowadays, they are Chinese brand also. There are many brands coming in India. But basically, these are three nice brands which people are mostly using in India, all around the world also. These are a deciding factor for designing and your chamber, for making a budget of your chamber, and it's a complete one for the far field anechoic chambers. Thank you very much. I've finished my presentation. I'm open for your questions and suggestions. My contact details are given here. Those who want to note, they can note down. Those who want to share and discuss anything with me can discuss and share. I would request for your questions and suggestions if you have any.
Thank you very much, sir, for sharing your knowledge with us. Now, questions will be posted on the screen.
So before that, a very big thank you, sir. I'm Raghavan. I've been enjoying your lectures. Still, many more lectures I will keep enjoying.
Thank you. It's my pleasure.
One cannot talk like you.
Sir, I'm Perumal Shankar, that coordinator of this program, sir. Welcome. Sir, I contacted you through our beloved professor, Dr. Raghavan sir only. Sir has given the guidance for this STTP.
Yes, I'm thankful to the sir also. I also got an opportunity to speak, and I really feeling good in front of your prestigious college, and especially in the south of, and that's too in Kerala. It's my pleasure to be there at this moment.
Through Dr. Shankar, I wanted to enjoy your lecture once again, sir. That's all.
Sir.
It's my pleasure, sir.
Sir is the reason for everything, sir. Sir is the reason for all the things. What is happening
yes.
here?
I know, sir, very well. So I can see some questions here. I would I try to answer one by one. Which material or chemical are used in RF absorber? See, the basic material is a polyurethane foam, but we are also using polyester and polyether foam. And then on this foam, we are impregnating chemicals like carbon. Carbon is most important chemical which is giving absorptive property. And in addition to that, there are various other chemicals which are responsible for fire retardancy, and that is also added. but all these are added in some ratio and proportion. We cannot make absorber completely fireproof by adding. We can do that by adding more fire retardant chemicals, but when you add more fire retardant chemicals, you are affecting the reflectivity of RF absorber. Next, please tell practical steps of radiation pattern measurement using anechoic chamber. Sir, it will be a different lecture on this, because a complete positioning system and all those I have to tell. I can, even if it is required, it can be shared on the mail.
Maybe
To get
my humble request to Professor Shankar, in your third page, I request you to include the second part of his wonderful lecture.
Okay, sure, sir. Sure, sir. That is our that is this thing, sir. Sure,
I
sure,
will
sure,
give
sir.
you,
You'll include.
sir, in that I will give you a complete demo. I can do that. I think I have to make the demo also of different tests to be done on the antenna by using the software and antenna positioner and anechoic chamber. So certainly, if that when the opportunity come, I will prepare and I will be delivering that. Thank you.
Sir, our request, we will be having one more phase next month, sir. We need your support in that, sir.
Okay, certainly. Okay. Then to get expertise in this unique field, did you have initial training anywhere, sir? See, whatever experience I have shared, nobody is giving training on this. It's the own experience, reading books, working with different experts in industry. Then all these things came. So it needs a little experience also. So there was no training given to me. Then compared to transmitting side, receiver side, RF absorber height, large, any specific reason, if it is possible to measure near field. Okay, first the response of the first part is yes. The major lobes and the high power will be in the front side of the transmitting end. So that portion should have a bigger absorber that is more responsible for the bandwidth of an antenna and for your other properties. For the side lobes and for the back lobes, the absorber size, absorber height is less. They are not affecting much. But on the major speculative zone area, one should have the bigger absorber depending upon the height which I have shared, lambda by 4. Then next part is it possible to measure near field region? Yes, we can measure near field region. Certainly we can do that, but we should have different test equipments for this. Your scanner and other things are also required. What is the next question? Why people not go for 3D gain measurement using anechoic chamber? See, it depends upon the user who needs, he will go, and who doesn't, he won't. The research which is not required will not go for that. There is no specific reason. Why only horn antenna is used as a reference antenna for measurement of radiation pattern? Why only horn antenna is used as a reference antenna for measurement of radiation pattern? I need to check the response of it, but mostly horn antennas are only used. I'll find out and I will be informing you. So I think these are the only 6 questions, sir.
Yes, sir.
Okay. So in case if you have more questions, then please let me know.
Thank you, sir. Thank you very much for a very informative session. So
Yes.
there are no more questions, sir. So we'll be winding up the session. The next session is scheduled at 11:45 a.m. Thank you very much, sir.
Thank you. It's my pleasure. And thank you very much all for listening me and giving us an opportunity. So at the end, I will say we have designed and manufactured very cost-effective solution for engineering colleges. And those engineering colleges or researchers, those who are looking for a good quality or less important is the cost also, less cost equipment, then all those were designed specially for academia by us. We'll be certainly supporting you. Do contact us and we'll be there with you. Thank you very much. Thanks a lot.
Thank
Thank
you
you,
so
sir.
much, sir.
Good morning, sir.
Very good morning, madam. Very good morning.
Sir, we'll be starting the session shortly.
Yeah, all right, all right. No problem. I'll just wait for the participants to also join.
Okay,
Then
sir.
we can take it forward.
Okay, sir.
Yeah, thank you.
Welcome back. Now we are entering the second technical session of today, which is based on design and analysis of planar monopole antennas, present and future aspects by Dr. Sandeep Kumar P. Dr. Sandeep Kumar P. completed his master's in communication systems and PhD in antenna engineering from the Department of Electronics and Communication Engineering, College of Engineering, Gindi, Chennai, and is working as assistant professor in the Department of Electronics and Communication Engineering at SRM University, Chennai. His research areas are planar antennas, monopole antennas, wideband antennas, conformal antennas, antenna measurements, microwaves, MIMO antennas, and 3D antennas. He is a strong proponent of the advancement of antenna education. Aside from his talents and advocacies, Dr. Sandeep Kumar P. has filed and published 11 Indian patents and has received an US patent. He is also a prestigious author of several IEEE journals, IEEE Transactions on Antennas and Propagation, IEEE Transactions on Vehicular Technology, IEEE Antennas and Wireless Propagation Letters, IET Microwave Antenna and Propagation, and various international journals on the subject of planar antenna design engineering and MIMO antennas. Dr. Sandeep is a reviewer of IEEE Antennas and Wireless Propagation Letters, IEEE Sensors Journal, IET Microwave and Antenna Propagation, Microwave and Optical Technology Letters, an international journal of microwaves and wireless technologies. He has conducted and served as a keynote speaker in several antenna FDPs and antenna design workshops. Now, I hand over the session to Dr. Sandeep Kumar P.
Yes, thank you very much, madam. Yeah, it's indeed very happy to meet the research fraternity, more specifically the RF research fraternity under this SCTP umbrella. Right, very happy to be part of this SCTP, and let me start with the session for this hour. So, yeah, yes. Hope you're able to see my screen.
Yes, sir.
Yeah.
So can you put it into slideshow?
Yeah, I will do that. I will do that. Okay, is it okay? Is it visible?
Yes, sir. Yes.
Okay, right. So, very, I can tell you good afternoon to all of you, right? So, I'm going to present on design and analysis of planar monopole antennas, right? Where are we today? And I'll be talking about the future aspects of the same. Right. I am Sandeep, and I am actually working for Saram University, Chennai. And I have completed my master's and PhD completely with respect to antenna engineering. And I'm a product of CEG, right? Under the guidance of Dr. K. Malti, professor in our University, Chennai. Right. So let me start on with today's presentation. So today I'm going to talk about, I think yesterday's session, you would have heard lots about the planar antennas, the different configurations of planar antennas and so on. Again, let me start our presentation with the concept of planar antennas, the different planar antennas, the planar monopole antennas from those different planar antenna configurations, then the applications of the planar monopole antennas. What are the recent research which is happening in your planar monopole antennas? What are the future aspects? And what all you should do? What do's and don'ts with respect to the design aspects of your planar monopole antennas? Next, with respect to the analysis part. Then I will be talking about several research papers. And in those research papers, I would be talking about the most important aspect of your design of planar monopole antennas, more specifically with respect to a single term, which is called as loading. And then I would be talking about MIMO antennas, vehicular antennas, and then I would be concluding my presentation. Right. So with this introduction to what I'm going to present today, let me start on, or let me just brush up with whatever has been happened during the last session, yesterday's session. Right? I think yesterday's session, you would have, professors would have been talking about planar antennas. And let me start on with the same. Right. So what are planar antennas? Right. So more specifically, a planar antenna is an antenna which have all its components. More specifically, you'll be having the substrate, radiator, ground plane, and the other parasitic elements on a particular plane, on a single plane. Next, why do we go in for these planar antennas? In the recent trends, we are there towards a miniaturization. And everything we want it in the case of a very small size objects, or small size gadgets. For that reason, these planar antennas have been evolved since 2000, and it is still ruling the RF market. Here, very small size is the main aspect for going into your planar antennas, and with a single term, which is called as miniaturization. The other advantages, low cost, low weight, low profile, ease of fabrication, all would be corresponding to the substrate what we choose. And it depends upon the applications. If you would like to use the antennas for a rigid applications, or I could call it as on a planar plane, right, or on a simple plane, or a simple rigid structure, then you will be using some rigid substrates or non-flexible substrates. And you can go in for cost-wise. Generally, we are using for this rigid substrates, we'll be using the substrate which is called as FR4 substrate, right? It is actually flame retardant of the order 4, and it is having an epsilon R 4.3 or 4.4, right? So here, when you're talking about the substrate, the choice of the substrate is very, very important when we are talking about the applications, number 1, and when you're talking about the cost factor also. And the other case is, these antennas can be used in for bend scenarios or flexible scenarios or conformal scenarios, or you can use it for flexibilities. For example, if you take it for your wearable applications, right? Of course, when you're keeping it on body, you should have that kind of a flexible nature, right? So for those reasons, you will be using over there some soft flexible substrates. Most commonly used material for a wearable is actually your jean material, right? And generally, we should not call it as like a particular jean material openly. It is actually a material with epsilon R of 1.7, right? Generally, when you're calling the substrate with the common terms like jeans and all, it doesn't look good. So we'll always tell jean substrate with an epsilon R of 1.7, right? So next one, we'll be going on with the basic planar antenna structures. And we know that in our normal antennas, your wire antennas and so on, you have only 2 structures, right? The basic antenna systems or basic antenna structures, right? Based upon the length, lambda by 2 or lambda by 4, we can call it as a dipole antenna or a monopole antenna. Yes. So here, let me take you on to this particular slide, right? So here you have a dipole antenna, right? I hope my pointer is clear. Is my pointer visible?
Yes, sir. Yes, sir. It is visible, sir.
Yes. Okay. So here, you know, we are just giving a feed over here. Okay, it is actually center fed, and this is having a length of lambda by 2. Right. So when it is having a length of lambda by 2, it will be corresponding to a dipole antenna. Yes. If I'm feeding it over here, the current would be minimum. It would go to the maximum at the edges, and then again it would come back to the minimum. So thereby you'll be getting a dumbbell shaped or an H shaped. Now, in the case of your lambda by 4 is actually half of your dipole antenna, right? Which is actually lambda by 4. Now, what I'm going to do is that I'm going to slice this. It is just an imagination, right? I'm not going to exactly tell you that it's just an imagination. So here, what we're going to do is that we are going to have a mirror or a ground, which will be covering this lambda by 2, right? So when I'm covering this part, what happens is that when I'm covering the bottom part, this particular one will become bottom fed. When this becomes bottom fed, you will be able to see only a round. But here I told you, this ground plane will act like a mirror. For that reason, whatever is over here, this particular radiation would be superimposed on this particular above a length of lambda by 4, and thereby the resultant would be a circular shaped. I would call it as an omnidirectional pattern, right? Now here, if you see, the length is lambda by 2. What about the ground plane? There's no ground plane. What if it is actually a balanced line, right? What about over here? Here, the length is a lambda by 4. It is actually sliced part of this. It is actually for the understanding I have just depicted in this way. And then what happens is that whatever is below, it gets superimposed on this particular radiation itself. So when it gets superimposed, what will happen is that this radiation would be like almost like double, and it will be added or summed up along with this on the top of this particular lambda by 4 region. So here, more specifically, I wanted to indicate the omnidirection pattern. we always, although we are there in the teaching line and teaching, and we are, I think research scholars are also part of this SCTP, right? So they are going to be future teachers also. We should never make a mistake that omnidirectional pattern means it is the radiation or equal power in all directions. No, it is wrong. We should never call it as equal power in all directions. Equal power in all direction, it is actually corresponding to an isotropic antenna where in all directions you will be having the equal power, which is an ideal source. Whereas here, what do you mean by monopole, or what do you mean by your, what do you call this, your omnidirectional pattern is that there will be equal power in one particular plane. We always get confused that omnidirection means equal power in all directions. No, it is actually equal power in one particular plane. This is the most common mistakes which we do even while taking the lectures, right? So with these basics of a normal wire antenna of length lambda by 2 and lambda by 4, let me go on with respect to our planar antennas. Here, if you see, we have had, depending upon the ground plane, probably the configurations, we have categorized as length lambda by 2 is dipole, length lambda by 4 is monopole. Similar way, here in your planar antennas, we have three kinds, right? One is a planar monopole antenna, planar dipole antenna, yes, corresponding to lambda by 2, lambda by 4, yes. And there is another one which is called as microstrip patch antennas. How do you differentiate between these planar antennas? It is with respect to the ground structures, right? It is for your understanding. If several antennas are being placed, and if you're asked to identify what is the antenna, what kind of antenna it is, you should be able to tell whether it's a planar monopole or a planar dipole or a microstrip patch antenna, right? So let me start on with the microstrip patch antenna. Here, if you see in planar antennas, the most common elements are your substrate. In general planar antennas, you'll be having your substrate, your feed as well as your radiator, and your ground plane in general. In your microstrip patch antenna, here, please note, you'll be having a feed, the patch, right, which is your radiator. You're having a substrate, and the very important one is you're having a complete ground plane, right? You're having a complete ground plane. So if you're having a complete ground plane, it comes into the general configuration of microstrip patch antenna. Here, since it's having a complete ground plane, the radiation, how it will happen, right? If it is completely grounded, from where the radiations would happen? It is with respect to the term which is called as fringes. It is mainly because of the fringing fields, right? Which is coming out of the edges of the patch antenna, or edges of the patch structure. Now, if I am partially cutting this ground plane, or generally what I'm doing in this case, right, over here, what are we doing? We're actually slicing this half, right, to get a lambda by 4. So similar way here, what we are going to do is that we are going to create a partial ground plane, and that partial ground plane is what has been shown over here. If this is a partial ground plane, maybe it may be approximately equal to lambda by 4, giving a space for the radiator. This particular configuration would be called as a planar monopole antenna. So whenever you're talking about planar monopole antenna, whenever you're seeing a partial ground plane, it would be corresponding to a planar monopole antenna. The next one is a planar dipole antenna. Here we don't have, so generally in your, here are you having any kind of, what do you call this, for better understanding, did you have any kind of ground plane? No, we did not have. So here, in this also, we have a ground plane, but please note, it is actually a balanced line to give the division of the dumbbell shaped, right? And of length of lambda by 2. So these are the basic structures which are there for your microstrip patch antenna, monopole antenna, and your dipole antenna. Depending upon the radiations, we can categorize it as narrowband, wideband, extremely wideband, super wideband, and etc. Now here, in your microstrip patch antennas, right, the one which I'm showing right now, this I have told you, it is actually complete ground plane. So when it is having complete ground plane, where it will be, which is corresponding to radiation, it is mainly because of these fringes, right? So it is because of these fringes that this antenna would be corresponding to a narrow band antenna. It would give you a very, very narrow band. And still, research is going on under this microstrip patch antenna for the bandwidth enhancement. There are several bandwidth enhancement techniques which will be corresponding to your microstrip patch antenna. Right. Now, with respect to your monopole antenna as well as dipole antenna, right, here you're having a partial ground plane and here you're having actually a balanced line. Right. So probably in the upcoming slides, I will be detailing telling you about what is happening with respect to the bandwidth and so on. Or probably let me start on with this slide itself. If you see over here, right, you're having a partial ground plane, right? Immediately after the partial ground plane, I would call this region, right? Immediately after this ground plane, I would call this region as a flooding region. I would almost equal to the tap which is open, right? So once you open the tap, it will immediately flood. The current path over here would be in such a way that this is actually a flooded region. So why I call this as flooded region? Because it is because of this current path that this particular point will help you in the traveling of the current throughout the structure. And it is very important that this small spacing of P, right? I have named it as P. Upcoming slides I would show you that this small spacing is very, very important for your wide bandwidth nature, right? It is not only that why this corresponds to wide bandwidth, because here one you have a partial ground plane and everything will get flooded and you're giving a large space for your radiation to happen, right? And large number of resonances would be there, and this would be corresponding to a wide band. More specifically, you are actually decreasing the Q factor, right? When the Q factor is decreased, right, even for your small antennas, right, when your Q factor is decreased, what will happen to the bandwidth? The bandwidth will enhance. Now, in the case of your dipole antennas, yes, here, since it's having a very small ground plane and so on, it would be giving an average bandwidth, a narrow band or a wide band, it will be in intermediate sector, right? So depending upon the ground plane, here we have categorized it into microstrip patch, monopole, and dipole for your understanding. Now, let me go on to the next part. Right? So this is just a gist of whatever I have told you. Right here, the microstrip patch antenna, the most what do you call this? I would tell you the Bible for this microstrip patch antenna would be the Balanas text, right? And it would have been explained in a very beautiful way. The next one is your dipole antennas, which I've told you with respect to lambda/2, and you'll be having a dumbbell shaped. Next, moving on to your planar antennas, I've told you it is actually a bottom fed, and here it gives you an omnidirectional pattern, and more specifically, this will result you in a wide band frequencies. Now here, why we go in for monopole antennas? If somebody asks why monopole antennas, the very first thing should strike in your mind is that it is mainly because it supports the wideband technology. Why? Because our monopole structure with respect to lambda/4, with respect to partial ground plane, and with respect to our what I call this flooding region, everything corresponds to our wideband technology, and it provides a wideband nature. Then, why do we go in for wideband technology? Mainly because you have several applications and high data rate applications which mainly deals with a wideband nature. Here, when I call it as wideband, I not only talk about wideband, I'll be talking about wideband, ultra wideband, super wideband, or extremely wideband. Now, when I'm talking about wideband, it may have a bandwidth of around 500 megahertz. Next, when I'm going on to ultra wideband, it has a bandwidth of 3.1 to 10.6 gigahertz, and it has been actually what you call standard, which has been given by FCC. Right? It is from 3.1 to 10.6 gigahertz. Next one is super wideband. The antennas which possesses a bandwidth of the ratio 1:10, a minimum of 1:10, where 1:10 corresponds to FL is to FU, then that particular antenna is what we call it as super wideband antennas. More than ultra wideband or near to super wideband, we always call it as generically, it is actually extremely wideband antennas, right? So all these wideband techniques or all these wideband frequencies are obtained with respect to disturbing the normal nature of the monopole structure. I would tell you in the upcoming slides. So now when I'm talking about these applications, right, we have radar applications, communications, intelligent sensors, medical applications, and home applications. In your home applications, I would rather talk about the IoT, right? The next one is, in your radar, you have ground penetration radar, through-wall radar, automotive radar, and so on. Communications, yes, we have our wireless USB, right? All our wireless technologies, which all uses high data rate. Sensors, yes, we do have it for telemetry, and we have it for our, what I call this, the technologies which are with respect to RFIDs. Then we have the intelligent transport systems. Medical applications, yes. This is another important aspect, medical applications, where recently it is in current trend, right, to identify the tumor, or to identify the lumps or masses, bone fracture detections, right? Everything are possible. You're using this particular monopole antenna, and which comes under your medical application umbrella. The next one is your IoT, which actually has many applications, right, integrated. Right. So we have all worked with communication, sensors, medical applications, home applications. Now we are actually doing our particular research in SRM with respect to the radar. We have not yet touched upon this radar. We are going to start, and we've already completed, or we are still in the evolution process of these communication, sensors, medical applications, and home applications. So now let me move on to the design analysis aspects of your planar monopole antennas. Here we have a feed line in general. Okay, this is just a general structure for your monopole structure, right? Here we have a feed line. We have a ground plane, which is actually, I would call it as a partial ground plane. I am not exactly naming it as a length of λ/4 for this partial ground plane. Why? Because when you're tuning or when you're doing the analysis, you will come to know that it may not be equal to λ/4 when you're obtaining your bandwidth. Right. So now here you'll be having a feed line, you'll be having a radiator on the top, a substrate below. Below the substrate, you'll be having a partial ground plane. In the several literatures, right, please note this spacing is very, very important. This spacing, right? The people who are doing research in monopole antennas and its applications, right, kindly refer to Professor K.P. Ray's paper, right, wonderfully explained regarding the basic structures of planar monopole antennas. And he would have given some equations also, and in that equation, right, he would have mentioned the importance of this particular distance, the flooding region. Right. So next one is here. I'm going to show some monoplanar monopole antennas. Right. If you see here, you're having the partial ground plane structures. Here also you're having the partial ground plane structures, and these all are the several planar monopole antennas, right? And here it may be fabricated on an FR4 substrate or on several Rogers substrate, right? Now, when I'm talking, as I've already mentioned, right, when I'm talking about your monopoles, the first thing should strike us, it is actually with respect to your wideband nature. So wideband, greater than 500 megahertz. More specifically, if it is an ultra wideband, it is 3.1 to 10.6 gigahertz. And extremely wideband and super wideband antennas would be falling under this cadre of 1:10. It should, the main thing is that it should have a good impedance matching, right, over the entire band of operation. And of course, small size, low cost, I've told you, these all with respect to the applications. Now, I would like to tell you, most important aspect is that the starting point of your feed line, it should be matched to a 50 ohms. So when you're talking about this 50 ohms, please note here, the starting should be with respect to a constant width, which means, let me tell you, it is actually called as width of the feed. This width of the feed is actually corresponding to your 50 ohms impedance matching. How? Because we already know that the 50 ohms impedance matching, or the Z naught or Z, would be with respect to, or as a function of, W by H or WF by H. W is nothing but here width of the feed, and H is nothing but height of the substrate. So if you take, for example, 4.3 epsilon R, which is your FR4 substrate, for 50 ohms matching, here the width of the feed for an height of the substrate of 1.6, this will be around 3 mm. Right? Please note the starting point is very, very important. And later on, you can have tapering of feed depending upon the design and depending upon the loading techniques which you're going to use. Very, very important is the starting point. In fact, several papers have come to me for review where this may not be of 50 ohms matching, and so that is of a concern, right? So this 50 ohms matching is must. So now next, moving on to the most important aspect with respect to the applications, right? So here we'll be talking about the simulation parameters, the simulation, what all are required, and with respect to measurements, what are required. It is always mandatory that whatever you're simulating, you will have to produce a validation with respect to the measurement results for your papers to be published in a very good journal, right? So let me start on with the rigid antennas, or the antennas which are fabricated on a rigid substrate, right? So here, basically, we'll be talking about S11, right? This mistake also I have seen that, S11 is being called as a return loss. Please note, for a single port antenna, and your antenna more specifically, here we call it as reflection coefficient, right? It is not correct, or it is not right to call it as return loss, because it is not a multi-port device, all right? So here we specifically call it as a reflection coefficient, right? After we obtain this reflection coefficient, it is mandatory to check the radiation performance, both in E plane and H plane. When you're talking about your, what do you call this, your monopole antennas, your H plane would be having an omnidirectional pattern. So what is an omnidirectional pattern? Equal power in one particular plane. Please note, not equal power in all directions, right? We always tend to tell that, right? So here, H plane is actually in one particular plane, omnidirectional pattern. E plane is like your normal dumbbell shaped. Yes, we have our gain, realized gain, and efficiency. The next one is the most important ones for all these high data rate application antennas, or these extremely wideband antennas or wideband antennas, is that it is actually your time domain analysis. When you're talking about your time domain analysis, probably till about 2012, 13, up till this efficiency part, the papers were getting published. But beyond, with respect to this time domain analysis, beyond your 2012, 13, right? Without the time domain analysis, the papers on monopole antennas, simple monopole antennas, are not getting accepted, right? It is mandatory that you will have to do the time domain analysis. So what is this time domain analysis, right? We are going to show that The pulses are intact over the frequencies when it is transmitted from one particular antenna to another particular antenna. Here, more specifically, we replicate the same antennas, right? So here, I'll be talking about S21. Please note here, for time domain analysis, I'm going to consider two antennas, more specifically, two similar antennas, whatever I have designed, and they'll be spaced at a far field distance. One antenna, another antenna, far field distance. And then what I'm going to do is that I'm going to measure the transfer function or the transmission coefficient. Please note, these are two separate entities. This is one antenna, this is another antenna. They both are not lying on the same plane. They are with a distance of far field distance. It is actually a system. What is the transmission coefficient, right? For that reason, I am not calling this S21 as mutual coupling or isolation, right? Here, I'm calling it as transfer function or a transmission coefficient. If you see, when you're measuring this transmission coefficient from this point to this point, with respect to the identical antennas placing face to face or side to side, you will notice that over the frequency range of operation, the S21 will be frequency flat. The S21 will be frequency flat, right? Which means that all the pulses are intact and they are remaining in this particular frequency range and they transmit in a very good go. Right. Next one, phase of S21. When I'm talking about phase of S21, here it should be linear, right? The variation should be on a linear note. If you're having the undulations, then you can tell that at that point or at that particular frequency, the impedance is not matched and the transmission is not happening in a very good way. The next one is your group delay, or even before the group delay, I would take about the another term, right? It is with respect to your the pulses which are transmitted. Pulse from this point to this point, right? When you're overlapping these pulses, you would see that almost it will be overlapping when the when the normalized graphs are used, right? When the normalized graphs are used. The next one is with respect to group delay. Here, the group delay variations should be very minimal. It should be in nanoseconds, right? I would tell it as group delay variation, right? Which means the to and fro, the group delay, right? That variation should be less than about 1 nanosecond or 2 nanoseconds. Even now we have somewhere around 0.25 nanoseconds and so on. The next one is fidelity factor. The very important point is fidelity factor. Now, in this fidelity factor, we will be talking about the maximum value of the cross correlation between the signals. Correlation should be there. The cross correlation should be maximum, right? So, which means the maximum value of this particular cross correlated value or the fidelity factor would be unity, would be 1, right? Here you want the system, that is your antenna, to transmit in an efficient way. So how do you find out? If the fidelity factor is very high, if it is close to 1, then we talk about that this particular antenna possesses a good time domain analysis. So under time domain analysis umbrella, we'll be having our S21, your transmission coefficient, your phase of S21, group delay variation, and the fidelity factor. So this is with respect to rigid antennas. Next, when we are coming on to the variable antennas or the flexible antennas or the antennas which can be used in for your conformal surfaces, we will be starting on with the further expansion of our reflection coefficient analysis with your conformal or the non-conformal nature or on-body scenarios, conformal and non-conformal, and more specifically, it will be with respect to bending analysis, right? S1 on flat surfaces or on a flat, flat surface, how it is. When it is bent with different angles or bent with different radius, right? How the reflection coefficient varies. When you're actually simulating your flexible antennas or more specifically variable antennas, when you're talking about this human body and on-body applications, here, generally, you will be designing the antenna on a wearable substrate, right? Next one is you'll be taking it closer to some tissue models, right? Skin, fat, muscle, and bone, right? And we'll be having the voxel models and so on, and you'll be doing the analysis. Now, there is one more type that you keep it near to the body itself or keep it along the tissue model itself, and then you design the antenna. One is separately you design the antenna and do the analysis over the on-body or with respect to bending scenarios over the body. The other one is you keep it very near to the body structure and then you design the antenna. There is actually a difference between this. When you're designing the antenna in free space and then you're taking, your reflection coefficient may change. That should not be the case. So for that reason, what do? You actually keep a spacing with an optimal spacing where your reflection coefficient will not vary. In the case of your antennas, which are designed very closely spaced to the human body or almost very near to the human body, then you design, there you will be not having the reflection coefficient variation because you are actually designing for those frequencies very near to the human bodies, and your intended frequency of operation will be corresponding to whatever you're going to design, right? So here we will be talking about reflection coefficient analysis, on body, off body, bending analysis with respect to several radius or with respect to several angles, and we would be telling that a good research, would be telling at the end, how far your antenna would be working, right, with respect to your bend scenarios. So you can tell that, beyond about 60 mm of radius, right, the antennas may have some deterioration in your S11 values, right. The next one is similarly, we'll be having the radiation pattern, right, E plane and H plane. Yes, bending analysis can be also carried out, and you'll be able to carry out the radiation pattern measurements in an anechoic chamber. Gain, efficiency, yes, these are normal values. More specifically here, when you're talking about wearable applications, the most important point which comes into our mind is our SAR analysis. It is actually your specific absorption rate. So what is the specific absorption rate? This is actually a parameter which tells you how much amount of energy or how much amount of power is being transferred to your body, right? So here, it's according to FCC IEC standards, right? It is actually 1.6 watt per kilogram for 1 gram of tissues, and for 10 gram of tissues, it is 2 watt per kilogram. So here, if you find, so first what you'll be taking is that you'll be taking that antenna and you will be doing the SAR measurements or SAR analysis with respect to simulations, right? Next, what do? You will be performing, in case if it is beyond the level of the SAR values which is prescribed, or which is 1.6 watt per kilogram for 1 gram of tissue, or 2 watts per kilogram, 2 watts per kilogram for 10 gram of tissues, then what do? You bring in these terms, which is actually your EBG, or your metamaterials, or you can bring in the FSS offices, right? For what? For reduction of your on-body penetration, for reduction of your SAR, right? So our main target is when you're going for wearable antennas, this should be completely below 1.6 watt per kilogram for 1 gram of tissues. Right. Next one is with respect to the communication aspects, we have our diversity antennas. Right, we have our diversity antennas or monopole antennas, right? When you're talking about diversity antennas or monopole antennas, why do we have these kind of diversity antennas or multiple antennas, right? Here, please note, it is not like a normal array structure where a single feed, from the single feed, it will be fed in for several radiators. No. Here, separate feeding mechanisms will be there. Separate feeds would be there for the antennas, right? So why do we go in for these diversity antennas? More specifically, in your receiver side, if you take about the antennas, right? If you're going in for multiple antennas, your signals may take several twists, turns, multipath mechanisms, or multipath channels, or multipath surroundings, and then it may come and hit your receiver. So here, let the signal be however worse, or let it take how many number of turns, twists, let it come. At least one antenna in this diversity set would receive the signal in an efficient way. This is the main concept of your diversity antenna. So when it comes means, like what happens is that, so here at least one antenna would be receiving in an efficient way. When you're talking about diversity antennas will be with respect to only your receiver side. This is very, very important. MIMOs, transmitter as well as receiver. Diversity, it is with respect to your receiver side. So here we are not talking about single port. Here we are talking about several ports. So depending upon these several ports, we will be having one reflection coefficient when you're talking about that particular antenna itself. The next one is, since they are placed on the same substrates, the intermediate spacing would result in a mutual coupling, right? Mutual coupling of these elements. So there we'll be talking about mutual coupling, which is actually your S21. Please note, S21 would be corresponding to mutual coupling as well as isolation. Mutual coupling will be called in terms of negative, in terms of dB. Isolation is a positive term, right? When you're talking about isolation, you please don't bring about this negative terms. That is very, very important, right? So mutual coupling, it is with respect to negative terms. Isolation, it is with respect to positive term. And of course, we have the reflection coefficient analysis. So here in your diversity antenna, we have our single port gain, efficiency, and so on. Next, we have the most important one is our envelope correlation coefficient, diversity gain, and the channel capacity. You'll be having your torque values and so on. Here, more specifically, we should not have correlation between these signals. Whereas in this case, in your time domain analysis, we should have maximum correlation, right? Here, we should have minimum correlation between the signals. For that reason, the envelope correlation coefficient should be close to zero, right? If you're having large number of spacing, of course, with respect to the spacing aspects, your ECC would vary. If you're having a large spacing, you'll be having very low ECC, and a very low ECC is only what wanted for your diversity antennas. More specifically, your diversity gain would be corresponding to 10 into square root of 1 minus rho square, where rho is nothing but your ECC. So ECC, when it is very small, your diversity gain would be approximately equal to 10 dB, right? So here, very, very important things which I would like to tell you is that, please, I would request all the researchers to kindly go through Professor Sharavi's paper, I think in 2017, where he has mentioned about the misuses and the misconceptions in our MIMO systems or MIMO antennas, right? Where he would have told that ECC, generally, let me tell you this, ECC, it can be calculated using S parameters as well as radiation parameters. Radiation parameters with respect to E field as well as your fields concept. And for XPR cross polarization ratio of 1, 0, and etc. Right? So here, in your particular ECC value, Professor Sharavi, he has mentioned in that paper that it is always better to calculate ECC using your radiation parameters or radiating fields or your radiation patterns. There, the radiation pattern should not overlap, right? It should have maximum, what do I call this, variation, right? If you're having the same thing, then
Hello, sir.
Hello.
Hi all, I'm very sorry. I'm very sorry. Actually, I think there is some network issues, right? I hope all of you are able to hear me.
Yes, sir.
Yes,
Yes,
sir.
sir.
Yeah, I'm very sorry. I'm very sorry. Yeah.
It's okay, sir.
Is my screen visible?
Yes, sir. Sir, can you please put it in slideshow
My
mode?
screen, yeah.
Yes, sir. We can
Yeah,
view.
I have already, yeah, yeah. Thank you. Thank you. Right. So here, when you're talking about these diversity antennas, right? I was talking before these network issues. I was just talking about Professor Sharavi's paper, right? It's very good. He has given lots of information regarding the misconceptions, right? I would just like everyone to give it a read on that particular paper, and I think it's there in IEEE Propagation magazine, right? And it's there in IEEE magazine. Actually, just give it a read. It's actually 2017 paper, right? So next, moving on to your applications, right? So here we have seen rigid antennas, right? We have seen with respect to our flexible as well as wearable antennas, the design and the analysis part. The next one is the diversity antennas, right? Diversity are your MIMO antennas, and we have seen the basic parameters like ECC, diversity gain, the channel capacity has to be calculated. So next is, in the recent trends, we are further having this particular automotive applications, right? In your automotive applications, if you see, you can place the antennas, or you have the antennas which is placed in this particular area. It is actually roof. These kind of antennas are actually called as shark fin antennas, right? So here what we can do is that we can actually remove the mold of that shark fin type, and we can integrate these planar monopole antennas, right? Either you can integrate a single, what I call as a single monopole antenna, or you can integrate the diversity mechanism, right? To encounter the multipath scenarios, right? Next one is with respect to the spoilers, right? Here you can have the antennas which is placed at these spoilers as well. You have the mirrors. Behind the side mirrors, you have a space, right? In that space, you can integrate these antennas. Bumpers. Here in this particular Volvo, you have the screen, right? You have the printed antennas, right? You have these lines you would have seen, right? So all these corresponds to the antennas. The next one is at the fender, right? Exactly at the fender side. Next. So these are the few popular antennas which we'll be using in for our automotive applications. So whip antenna, bee sting antenna, shark fin antenna, and you have your rear glass antenna. This was the thing which I was telling you about the sticker antennas over here, the lines. So more specifically, when you're talking about the shark fin antenna, right? When you remove this mold, you can actually have a space where you can integrate your antennas. Your monopole antenna, more specifically a unit cell antenna, or it can be with respect to your diversity nature, depending upon the size. Here, the most important one is the size is very, very important. It should fit into this particular size. Another thing is that here we should do the on-car analysis. On-car analysis means you're having a metallic body, right? So on metallic body, or the housing effects needs to be studied. Here, apart from all the other, analysis part, here, the most important one is housing effects for the cars also needs to be studied, right? So you'll be having a simple, block, right? A metallic block. And then on the top of that, you'll be placing your unit cell or your diversity antennas, and then you'll be studying the reflection coefficient performances. And it is not only that, here you have another space, which I have already told you, in your side mirrors, right? Behind the side mirror, there's a spacing. So here also you can study about the analysis, or you can study about how your antenna performs, right? When it is placed in this side mirrors. In your simulation itself, you can actually bring in your CAD models of the car, and you can integrate the antennas onto them, and you can check your simulations. The people who are doing with automotive applications, they do that, and they can bring in lots of analysis with respect to your radiation performances, with respect to your on-body analysis, with respect to car I'm talking about, right? And then so on. So here, to summarize what I have told you regarding the the rigid antennas, the flexible antennas, and diversity antennas, right? Here, I would like to tell you is that it is mandatory for an ultra-wideband antenna. When you're talking about ultra-wideband antenna or a wideband antenna, here I'm talking about monopole antenna, right? It is mandatory to show this time domain analysis, right? The next one is, after showing all these things, for your variable antennas or for your flexible nature, it is mandatory that you need to show the bending analysis, how far your antenna can bend. It is not only with respect to reflection coefficient, you'll have to show it with respect to your radiation pattern also. So in your current trend, okay, this variable antenna concept, the flexible nature, everything comes into picture. One more thing is also here in this variable antennas, right? There's one more small topic actually. It is with respect to your implantable antennas, right? Implantable antennas, which is inside your body, right? What all will happen when it is placed inside your body, right? Inside your body tissues, right? So for that, I think we have the sessions which is coming up, I think on Friday or Saturday, we'll be having a session, right? And the next one is with respect to diversity antennas, right? So here, when you're talking about your diversity antennas, for the unit cell, please note you will have to carry out all these things, and then you will have to talk about the S parameters of the entire components, right? Or your entire, the diversity set, the radiation patterns, the gain efficiency, diversity gain, ECC channel capacity, and so on. Whereas for your automotive applications, you got to show all these things for the unit cell. Next, you will have to show the on-car analysis or the housing effects you'll have to study. Then, if it is a diversity antenna, you'll have to study all these parameters with respect to the housing effects as well. And then you got to study the radiation performances while placing it in the car, several places in your car surfaces, and which can be done as a simulation study, right? With respect to this, simulation study on car analysis or on the body parts, right? It is very much appreciated, and in your IEEE transactions on vehicular technology, this is what they do expect, all right? The next one is with respect to your popular antennas. I've talked lots about the application point. Now let me talk about certain design aspects, some basic designs, right? With respect to the concept which is called as loading, right? So what do you mean by loading? Loading is actually disturbance of natural resonance. We always hear this, from several people that, antenna means you do randomly and you get the answer. No, it is not so. It is not a random performance. It is the term which is called as loading, and it is corresponding to your inductance loading or your capacitive loading. It is depending upon this inductance loading or your capacitive loading that you're tuning your frequency to your whatever the frequency you really require or what the application wants, right? So for that, what do? We talk about the term which is called as loading. So let me take few examples of the antennas which is being shown over here, right? Here, if you see, they have just taken a simple structure, right? They have just taken a simple, what I call this, a square-shaped structure. And here, there are lots of spacing between your radiator as well as your ground plane part, right? And here they have mentioned a small step. If you go through several literatures, there are several techniques corresponding to a better impedance matching throughout the band, as well as a better bandwidth performance. So here, this stepping or this stepped feed, okay, this would correspond to a better bandwidth enhancement. And then the next part is with respect to defected ground structure. In your ground, you actually defect some parts so that this would create a resonance where your impedance is not matched, and then that resonance will pull down all the frequencies to give you a wide bandwidth. The next one is with respect to your enhancement of your radiators. Please note, I would always tell that when you're talking about monopoles, please do not call it as patch element. Why? When you're talking about patch element, immediately it strikes is that you are actually having a microstrip patch, means it's like full ground plane, right? So for a monopole antenna, please do call it as a radiator only. Please call this particular portion as radiator, right? Please do not call it as patch elements, right? So now here in this radiator, it is actually a simple shaped. Here we have just used this kind of a normal technique with respect to your stepped performance, your stepped loading. The next one is with respect to your, what I call this, defected ground structures, right? Then they have bought some parasitic elements. I will tell you why they bring in these parasitic elements and what it exactly does in the upcoming slides. And over here in this paper, right, in this particular design, right, here they have shown a clover-shaped structure or a clove-shaped structure with a defected ground structure and a semi-elliptical ground plane. Over here, if you see, they have actually induced a neck, or they have just tilted a part of the path with respect to your feed, right? And they were able to obtain a better bandwidth. Over here, you're having a defected ground structure at the back with respect to slits as well. Over here in the front, this is actually with respect to your radiator. And then they have etched out some portions. And again, further, they have etched out some portions. What does it exactly do? Now, here, if you see, with respect to bandwidth enhancement, means either you can move your lower cutoff frequency to the lower values, or moving up your higher frequencies to higher values, which means you're actually pulling down the resonances. The next one is, or if in case if there is some impedance mismatch with respect to the intermediate frequencies, you actually pull those frequencies down. That's what we are actually doing it with this loading aspect, which is actually your disturbance of your natural resonance. Right. So here, more specifically, generally, if there are two plates and if there is an air gap, right, what do we call it as? We just simply call it as a capacitor, right? So here also, if some part is etched out, here more of capacitance effect would take place. But this capacitance effect, how it is varying with your design, it will be varying from person to person. It is not a fixed variation that you do this particular loading, you'll be able to get it. You do the inductive loading, you'll be able to get it. No. If there are some particular design aspects, when you go through the papers, you will understand that some kind of inductive loading, okay, when you're doing it on the radiator side, there will be a shift in the lower cutoff frequencies. For example, if we take, here this particular, what do I call this? This particular antenna, right? It first started with an ellipse, right? So for an ellipse, if you see the deflection coefficient below minus 10 dB, it would be from somewhere around 4 gigahertz or 3.5 gigahertz, and see the performance. It's going above the frequency is greater than 30 gigahertz. Here, our main aim is that to be called as a super wideband antenna, the frequency should be having 1:10 ratio. So here, to validate it for 30 gigahertz, right, what should be the starting frequency? It should be somewhere around 3 gigahertz. So if it is radiating from 3 gigahertz to 30 gigahertz, which is having a ratio of 1:10, then that antenna can be called as a super wideband antenna. So here, what we are trying to do is that we are trying to push this to lower cutoff frequencies. We just want the better impedance matching, and we want these resonances to be happening at the starting from 3 gigahertz onwards. So what we have done is that we have loaded on with the 2 more ellipses in a particular fashion, so that the current path gets increased. When the length increases, what will happen to the frequency? The frequency would get shifted towards the lower side. So here what will happen when it shifts to the lower side, right? You will be able to get your desired band. So further we have done while integrating these 2 ellipses in this fashion, we were able to obtain somewhere around 3.5 gigahertz. Further, we have integrated, because our main intention is to obtain from 3 gigahertz, right? So what we have done, we have further enhanced we have integrated 1 more ellipse in the vertical fashion, and then what happens, the current path is further increased, thereby here this has been reduced to a lower cutoff frequency, and we were able to obtain the blue color line, we were able to obtain it from somewhere around 2.95 gigahertz till the frequency which is greater than 30 gigahertz. Next, if you see the defected ground structure over here, right? If you see the defected ground structure over here, see, without the V cut, right, without the defects over here, you are able to get a small poor impedance matching over here, right, at somewhere around frequencies of 5 gigahertz. So with respect to the variation in the dimensions of this particular V cut, we were able to pull this resonance down so that this will be contained below minus 10 dB. So this is the main aspect of your defected ground structure. Please note, defected ground structures, it is not only corresponding to this V cut or your triangular cut or your, what I call this, your rectangular cut. It can be of any shape, but it should be pertaining to what you want, right? It should be pertaining to what you want with respect to frequency of operation. Now here, in this particular, this is actually Dr. Mohammad Sharavi's paper, not Mohammad Sharavi, I'm sorry, Dr. M. Ojudwi's paper. Okay, it is there in IIT Microwave and Propagation, as well as there are several antennas reported by Ojudwi, and it is there in IEEE AWPL also, right? And here, if you see, first let me start on with this antenna 1. Here, they have shown VSWR, right? Please note, if you are showing VSWR, please don't show reflection coefficient. Both of them, they almost mean the same thing. There, it will be below minus 10 dB, and here it will be contained between 1 and 2 VSWR values, right? So please show any one only, right? So here they have shown VSWR, which is from 1:2. And if you see here, the antenna 1, right? Here you are having actually a simple, what I call this, a square shaped structure with a stepped performance. You are able to operate a wide band, and you are able to see that beyond 10 gigahertz, they were not able to achieve the wide bandwidth. So what they have done is that they have done the defected ground structures. So to pull this particular frequency or pull this particular resonance down. So they have integrated these defective ground structures, and they were able to obtain this particular frequencies from 3 gigahertz to frequency greater than 20 gigahertz. Right. The next one is with respect to your what do you call this? These parasitic elements. The very important one is when you're talking about these wideband, extremely wideband structures or super wideband structures, there are several licensed bands within this unlicensed bands. When you're talking about extremely wideband, and so on, who is licensing it? We don't have licensed bands, right? It is actually an unlicensed band. You're covering for the entire frequencies, right? Extremely wideband and wideband. Right, we are just calling it as like what do you call it, greater than 500 megahertz, 1:10 ratio, and so on. But within this particular, you have several licensed bands. Even nowadays, the sub 6 gigahertz band is also coming under your 3.1 to 10.6 gigahertz range. And not only that, you're having your 5.2, 5 useful bands or licensed band, 5 gigahertz, 5.2 gigahertz, 5.8 gigahertz, and so on. So all these bands will have to be notched, which means all these bands will have to be notched so that there will not be any interference between these signals as well as the other signals which are actually using these particular licensed bands, right? So for that reason here, they have shown a particular notching which is somewhere around 5.2 gigahertz. And here if you see, it is mainly because of these parasitic elements, right? It is because of these parasitic elements. Please note, let me tell you one more thing. These are parasitic elements and these are not attached to ground planes. There are several papers, if these stubs are attached to the ground planes, they would be corresponding in for another resonance or for another bandwidth enhancement, or they would be helping in for mutual coupling reduction when you are going in for your MIMO set or your diversity set, right? The next one is with respect to, again, these notching structures only. Here, they have obtained a very wide bandwidth actually, right? You're able to see this for this gray color line from somewhere around 3 gigahertz or somewhere around 3.2 gigahertz till the frequency which is greater than 12 gigahertz. And then, if you see, they have etched out a portion from the radiator. So here, more of your capacitance effect to take place. Why? See here, a plate, another plate in between air, right? Generally, when you're talking about loading or whenever you're talking about your inductive loading or your capacitive loading, we cannot directly do a complete inductive loading or a complete capacitive loading. Associated to that, there will be, if you're having a maximum of inductive loading, associated to it, there will be a small capacitive loading also. When you're doing a maximum capacitive loading, associated to that, there will be a small inductance loading also, right? This thing you should understand. So by etching out two slots, one slot over here, another slot over here, they have obtained two band notches, right? The next one is, these are the recent research topics which are happening in your planar monopole antenna domain. So here we are having our rigid wideband monopole antennas, which I've already told you, and it is still working out, and still many papers are getting published, right, in the very reputed international journals. The next one is, of course, when you're going in for rigid, these both I would club it together, because now for the papers to get published and so on, right, these both would go hand on, they go hand in hand. Because this, when you're talking about your monopole antennas, there are several papers which are reported with monopole antennas, and if you're bringing in some good techniques with respect to your notching aspects, then this would be a good research proposal or research topic. The next one is your reconfigurable antennas, the most promising candidate for the future also, reconfigurable antennas. So in your reconfigurable antennas, you are having frequency reconfigurability, polarization reconfigurability, pattern reconfigurability, and a combination of all is also possible with respect to your reconfigurable antennas. The next one is wideband monopole antennas on flexible substrates. Please note, here also several antennas have been discussed with respect to these flexible substrates. Here, there's one more advantage is that you can actually do your time domain analysis, and I have seen very limited time domain analysis only done for these flexible substrates or these flexible monopole antennas, right? And very few researches have been carried out with respect to your MIMO domain also, MIMO or your diversity domain also with respect to these flexible substrates, right? So this particular topic, MIMO flexible antennas or flexible MIMO antennas, right? So this is another topic of interest, right? And over here, several analysis can be done, and not only analysis, several fabrication techniques also are there, right? When you're going in for these flexible substrates, you're actually having inkjet printed manufacturing things, right? You're having handmade prototypes, right? Several handmade prototypes. I will just show you some prototypes in the upcoming slides, right? And then you're having these diversity or MIMO antennas, which I've already told you, right? So now these diversity MIMO antennas would be always there because now you are actually entering into your 5G, right? Researchers are going on 5G and beyond. So there you require a massive MIMO antennas, right? Where it will be more of your what I call beam steering, beam scanning aspects, right? So all these things will be carried out in your MIMO antennas. So these are the few antennas, right, which are published in IEEE and several reputed journals, right? This is actually a palm tree shaped antenna, right? This was actually a very preliminary work which was just started in somewhere around 2011, and we were able to obtain around 4 gigahertz to somewhere around 10.4 gigahertz only. Then we went in for the super wideband antenna structures, right, from 1:10 ratio. So we have covered from 3 gigahertz to 30 gigahertz. Then these are the band notching antennas, band notched antennas, single band notching, and then you'll be having a dual band notching. Please note these notches, right? This length would be corresponding to the lambda values of your band to be notched, of your frequency to be notched. See, previously we were having a very wide band of notching, which means if you're getting somewhere on 5 gigahertz and you're not bothered about the bandwidth of notching, they just publish it. But now it is very much important that it should have a peak value of notching, right? Or because there are several papers which are reported with a normal notching, here you should have a very, very big kind of tuning nature. The next one, this is actually fabricated on a normal Teslin paper. This is actually a handmade prototype. This is actually a fractal structure, this and this one also. And here we have fabricated on gene substrates. So these are just few samples which we want to show you. Likewise, we have done around more than 100 plus antennas, right? And then this is actually a simple 2-port antenna structure, right, from this unit cell. Then this is actually an 8-port antenna. This is first of its kind when we designed it during 2016, 2017. And we started with this with respect to this 3D concepts as well as these MIMO concepts where, that was a time where, these massive MIMO things were also started, where more beyond 8 antennas, 16 antennas, 24 antennas, and so on. This will pave a way for that particular massive MIMO structure, right? These are reconfigurable structures, right? And then this particular one, it is actually for the flexible kind of scenarios or for wearable applications. So this is actually a denim material, right? More specifically commonly used as a jean material. It's actually denim material. Epsilon R is 1.7. This is actually a Teslin paper antenna, right? It is having around an epsilon R of 2. Polyamide, we are having it around 4.3 also we are having, and 3.5 also we are having polyamide. Polyester, it is somewhere around 1.9. So likewise, we have done several antennas on this, right? And here, this is what I was talking about. There are very less number of MIMO antennas which are reported for these flexible scenarios, right? When you're talking about these MIMO antennas, please, it's a humble request from my side, kindly go through Professor Sharavi's sir's paper, right? It is a very good one regarding the misconceptions of our MIMO antennas, right? So again, these are the performances as I have told you, right? And here I would like to show you that simple structure of that 8-port antenna, right? So here I would like to show you that. And here if you see, first we started on with a particular rectangular shaped monopole antenna, simple rectangular shaped monopole antenna. So this performance, obviously, since it's having a partial ground plane and a very small flooding region, this will result in a very wide band, right? So here, if you see, it is almost resulting in a wide band, but at this region, right, somewhere around, if you take the 10 dB line, it will be somewhere around this 10 gigahertz and so on. So later on, what we did was we increased the current path by slicing a part of the rectangular portion. Then the current path has been increased. Further, there's a reduction in your frequency, in your lower cutoff frequency. Further again, the current path over here is also further enhanced because we wanted for the frequency range starting from 3 gigahertz, right? We are very specifically over there. We want it from 3 gigahertz so that it will be covering our 3.1 to 10.6 gigahertz as well, right? So then next we will be having our our defected ground structure. So when we are having your defected ground structure, what happens is that this will pull the resonances down. A better impedance matching is achieved. So when a better impedance matching is achieved, you'll be able to see for antenna 4, which is a red color, the frequencies are pulled down when compared to your dotted red one, your green one, and the blue ones, right? You're able to achieve a better impedance performance. The next one is with respect to antenna number 5. Further, we are actually taking out a small portion so that your length would be increased. When your length is increased, what will happen? There will be a reduction in your frequency because we would like to obtain it from 3 gigahertz. And further, we have done a modification in the feed also. Please note, we have not disturbed this width of the feed because we want a proper impedance matching of 50 ohms at the mouth of this, right? This is very, very important, 50 ohms. Right, 50 ohms. It is actually width of the feed. This corresponds to height of the substrate and epsilon of the substrate. Right. The next one is over here. This I have already shown you. This is with respect to your closed structure, and this is already there in the International Journal of Microwave and Wireless Technologies, and this is there in IEEE antennas and wireless propagation letters. So these are the several notched antennas, which I have already told you. Why I have shown you this particular slide is that we always see that, when you're having your simulated and your your measured, there will be some variations, right? This is mainly because whatever the SMA connectors we are using, we have a limitation, right? Probably after your 6 gigahertz or 8 gigahertz, there are some limitations for your SMA connectors. We will have to use those SMA connectors wisely, number 1. Number 2 is that our effects, your fabrication errors, especially when you're going in for these variable antennas, there will be lots of undulations and lots of shift in frequencies also, because you may have cut using your hand, which is your handmade prototypes, or with respect to the boundaries which has been cut with respect to your tests and papers and so on, right? I have shown you over here, right? These all are handmade prototypes, right? These polyester, you'll be able to see the variations along the sides, right? And of course, these edges also, right? A small variation itself would result in the performance deterioration, right? Beyond that, you'll be having the bent scenarios. If you take this polyamide, right? Polyamide would be almost bent, right? So for that, you need to press the sides, right? Please note, here we have X bend and Y bend in your flexible antennas, right? When you're having your X bend, Y bend nature, if you're bending it towards or along your feed, obviously the feed lines would break. So again and again, you'll have to refabricate these things so that you get a better performance to study your bending analysis. Especially your bending analysis, please have about 2-3 prototypes ready, right, for it to be studied, right? The next one is with respect to your undulations and so on, right? The ground plane, whatever you're using, this is also there, right? In IEEE Transactions on Antenna Propagation by Professor C. Gabriel, right? He has told that when we are using this ground plane, right? This small ground plane is actually, when it is compared to the length of the cable which is used, it is very, very small. So this completely modifies the current, and thereby it results in a very poor performance in your measured result, or there will be a complete variation in your measured result, right? For that reason, he has suggested one thing, that if these cable losses are not there, try to connect it, okay, with directly onto your device, right? But generally we use our what do you call this, our cables, right, for better performances also, right, with respect to not deteriorating our devices for measurements, right? The next one is with respect to all these notching bands and so on. And then we have the flexible bands, actually flexible antennas. This is with respect to our, what do you call this, a normal test and paper. And here, if you see these graded papers and all, for bending analysis, what we do is that we will be having our, what do you call this, foam structures, right? So on the foam structures, we will be bending either on X bend or in Y bend directions, right? It is not only that, we will have to take in while fabricating these handmade prototypes, right? Either you can buy the conductive tapes, right? Conductive tapes, which is nothing but your copper tapes, and you can actually, what do you call this, cut according to the shape, and you can stick it. Number one, or you can take the conductive plates, and then you can actually use the conductive glues, right, to get it stuck onto your paper substrate. Right. So, but these all are like, the approximate things only, right? Because since it's handmade, right? So you'll be obviously having some variations in your measurement results, right? So these all are with respect to your, what do you call this, MIMO antenna structures, right? Here also 2-port MIMO antenna structure, right? And here, this is actually an 8-port, which I was talking to you about, right? So here you're having actually an 8-port, 1, 2, 3, and 4, right, along one plane. So here it is actually orthogonally placed, right? This is placed in this direction. This plays 90 degrees to this, 90 degrees to this, and 90 degrees to this. So here we will be dealing about one horizontal and one vertical, in a sense, 2 polarized vectors, 1, 2. Now the third one would be on the protruded version, which is actually along another direction, right? We have 4 antennas in this direction. So 4 over here and 4 over here, this would be corresponding to 8-port. This was actually in 2016-17, right? Later on, now we are into about 16-port and 24-port and so on, right? Then with this, let me complete the presentation for today, right? We have actually talked more about the planar antennas, right, and planar monopole antennas, the design aspects, and not only the design aspects, few do's and don'ts also we have seen. The most important ones with respect to these planar monopole antennas is that the width of the feed is actually very important. It is corresponding to your 50 ohms, and the immediate value, which is your flooding region, right, immediately after your ground plane, right, that should be also monitored, because that plays a very vital role for your bandwidth enhancement. The next one is with respect to MIMO antennas also, we have seen, right, and several present research areas we have seen, and the futuristic aspects also we have seen with respect to wearable technology, with respect to automotive antennas, all right. And recently we have the sub-6 gigahertz band also, which is coming in, because sub-6 gigahertz band, several countries, they use several frequency bands. And when you're going in for these wideband kind of scenarios, you can cover all the frequency bands, say somewhere around 3.4 gigahertz till frequency around 5.2 or 5.3 gigahertz. Because still it's not standardized, the frequencies are not still there, right? And then next one is with respect to how our antennas, how our monopole antennas, with the help of loading, how this, how we are actually disturbing the normal resonance to obtain wideband, ultra wideband, super wideband, and extremely wideband the scenarios, right? How we are actually obtaining this high data rate antennas, right? With respect to our MIMO antennas also we have seen. So each and every antennas would be corresponding to our wideband, ultra wideband, super wideband, whatever you have seen. The next one is band notching aspects, the flexible antennas, how it would be giving you, and very, very important when you're talking about your wearable antennas, please, you should take about, you can give about your limitations of this particular antenna, right? This antenna would be having it till around probably say with respect to some bending radius or bending angle. This is the limitation, likewise you can tell. The next one is with respect to the diversity antennas, right? You have polarization diversity, pattern diversity, horizontal, vertical polarization, right? And so on can be obtained. We have seen it using the 2-port as well as our 8-port antenna systems. So these are the several research papers. We have Ojudvi, right? Professor Ojudvi's paper. Sharavi sir's paper is also there, right? And then we have several papers, right, reported in our literature and in IEEE, AWPL, IEEE transactions on antenna propagation. When you're doing with respect to monopole antennas, I always request you to have this chart in your mind, right? It is actually this particular chart. If you want, you can just take a picture of this, right? So if you are actually having all these things, there are high probable nature of your research to get published in a very good journal. These are the mandatory things which is required for your monopole antenna designs and so on. All right. So with this, let me wind up today's session or the present session, right? And thank you, and I will open it for the forum to kindly shoot the questions.
Thank you very much, sir, for a very informative session. Sir, questions will be presented on the screen.
Okay. See, actually, the thing is that, like, I'm getting calls at 1:30. I'm having a board of studies meeting, right? So what I would do is that I will just answer a few questions, and then let me answer the few questions with respect to the mail or somewhere like that. That would be good.
Okay.
Yeah?
Okay, so that's okay.
Yeah. So the first question, let me take it up. It is actually differentiate a monopole as well as DGS, right? So monopole, I told you, it is actually with respect to the partial ground plane, right? I've already shown you in the structure. Defected ground structures are nothing but the structures which are actually, you either create some slots or some etch out some portion of the ground plane, so that that will result in another resonance, right? So here monopole is actually a basic configuration which is having a length of λ/4, and defected ground structure, it is actually with respect to your ground plane. You're actually defecting the ground more specifically, right, to create another resonance. Well, book for monopole, yes, there are several books available, but I would tell you, than books for the monopole, kindly go through the papers, the research papers, what all I have suggested right now, right? And of course, we have starting from what I call this, Professor K.P. Ray, Professor Raghavan sir, right? All these people, they have published very good number of monopole papers. You can in fact go through them, so that the physics of the antennas can be understood in a very well manner. Right. The next one is, sir, please provide some references for planar resonators. Yes, I would do it. Probably at the end of the session, I think, madam, you can just, I'll just post my email ID, right? And
Okay.
I can just provide some references and so on to them, actually, right?
Okay, sir.
And in case of any queries, you can actually call me and we can just do that. Yeah.
Okay, sir.
Okay. Yeah. What is the difference between planar antennas and printed antennas? See, you are having the planar antennas, right? Planar antennas, it is actually confined along one plane and so on. We talk about all those things. But printed antennas, more specifically, it is with respect to the fabrication point of view, right? More specifically, printed antennas means you have the etching process, right? All your MICs would come into picture. That is with respect to your printed antennas. The next one is reflection coefficient in terms of dB only, called return loss. Is it correct? I told you that, reflection coefficient, if it is with respect to a single port, right, we are actually, for an antenna, we are studying the reflection performance with respect to a cable, right? We are not studying any return losses, right? Return losses is for multi-port, right? Please understand that. The next one is, why it is said that time domain analysis is mandatory for printed monopole antennas. Yes, I've already told you the importance of printed monopole antennas is that when you're talking about the wideband antennas, in time domain, how it is very short pulses. But these pulses will have to be studied in such a way that whatever you're transmitting needs to be received in a proper way, right? So how you will be showing it? If you're showing this using this time domain analysis, it would be better that you can tell that the pulses are intact over the frequency band of operation, right? Next one is, what should be the permissible group delay for rigid antennas and also fidelity factor? Generally, for the fidelity factor, right, I told you it should be close to 1, right? It should be close to 1, right? When you're talking about fidelity factor means it is a maximum value of the cross correlation. Here, it is two entities. One is a transmitter antenna, the other one is a receiver antennas. And here, when it is placed far apart, it is on two different elements. You are studying the transmission. So here, the cross correlation should be good. So for that reason, here the fidelity factor should be unity, around unity. And here, the group delay variation should be less, somewhere in nanoseconds. And of course, group delay variation is nothing but the negative value of the differential value of your phase, right? So see, it is very, very important that if something is, seen a variation in your S21, in your transmission coefficient, if some variation is there, that will immediately affect your phase of S21. That will immediately affect your your group delay, and that will immediately affect your fidelity factor also. Similar way, if you see that if there is a variation in the group delay, if there is some strong disturbance in the group delay, and that particular variation would be reported in the improper matching with respect to your phase of S21, there will be some variations or undulations, and then further there will be variation in your S21, which is your your transmission coefficient. Right. So with this, I think I'm getting the other questions. I would request you to kindly post it to me using my mail ID, and I will just type it and I will just send it to you across.
Okay, sir. Okay, sir.
Right.
Thank you very much,
Thank
sir.
you very much for this opportunity.
For a very informative session. Thank you, sir.
Yeah, thank you. And I'm very happy, to be a part of this presentation. And I thank Pirimal sir for this particular opportunity. And I would just project my mail ID in case of any queries. Is my screen visible?
No, sir.
Right now?
Yes, sir.
Now it's visible?
Yes, sir.
Yeah.
Yes, sir.
If any doubts regarding this and for further collaborations and so on, you can 100% write it to me. And this is my mail ID, sandeep@srmist.edu.in, or this is my personal ID, vrpchs@gmail.com. Thank you very much.
Okay, sir. Thank you very much.
Right, and I'm very happy to be a part of this particular presentation.
Thank you,
And
sir.
particular STTP. Thank you.
So we are winding up the session now. The next session is scheduled at 2 p.m. Thank you for joining us.